In the depths of the constellation Cygnus, there is a star that flickers in a way that seems almost capricious. Its brightness fades and then brightens with no pattern that astronomers could recognize. A cosmic lantern that refuses to burn with a steady flame. Astronomers who lecture about the search for extraterrestrial life speak of this star as the strangest they have seen, because no other object in the Milky Way behaves quite like it. When its light dips, the fall is not a gentle dimming, but an abrupt plunge that would be alarming if this were a familiar friend. Watching such a star invites curiosity and a strange calm, as though the universe itself were whispering a secret. The star, known formally as KYC 8462852, shines as part of a binary system more than 1,000 light-years from our world. One component is an F-type main sequence star, the other a faint red dwarf, and together they orbit in the constellation Cygnus. To those who have followed its story, the star has acquired many names: Boyajian's star, Tabby's star, even the playful abbreviation WTF for Where's the Flux, all pointing to the same extraordinary question. The star's light can plummet by as much as 20% or more, a behavior unlike anything seen in other stars of this class. Citizen volunteers first noticed this behavior when they were combing through space telescope data, and their discovery quickly spread. The unusual dips in brightness recorded for this star startled astronomers because they were so deep and irregular. Some dips reached nearly a fifth of the star's normal output, far greater than the 1% drop typically caused by a passing planet. At first, researchers wondered whether something was wrong with the telescope or the instruments, but repeated observations showed the changes were real. Without an obvious explanation, they proposed possibilities as varied as giant planets, swarms of comets, clouds of dust, or even the speculative idea of some vast megastructure built by an advanced civilization. Each suggestion stirred the imagination, but none could fully explain what was being seen. The star's story begins with NASA's Kepler Space Telescope, which gazed fixedly at a patch of sky for years, measuring the brightness of over 100,000 stars in pursuit of distant planets. Kepler's method was elegantly simple. If a planet passed in front of its host star, a tiny dip in starlight would appear on the instrument's graph. By recording these small, regular reductions, scientists could infer the presence and size of worlds we could not see directly. Kepler had been designed to catch these fleeting shadows, so when its sensors recorded deep, erratic dimming from one particular star, the data stood out like an alarm bell in a quiet night. Though Kepler amassed the data, it was human eyes that first recognized the anomaly. A group of citizen scientists working with the Planet Hunters Project, an initiative that invites volunteers to examine light curves and flag interesting patterns, noticed the odd behavior in KYC 8462852. These volunteers were not professional astronomers, but curious individuals from around the world who took the time to sift through graphs of starlight in search of the subtle dips that hint at new planets. When they saw a light curve plunging in a way no planet could cause, they knew they had found something unusual. Their alert set the professional community in motion. Among the people drawn to this mystery were volunteers from unexpected backgrounds. One had once worked as a seatbelt factory foreman, another served as a safety and security coordinator, and another trained shop floor workers for a living. None were professional astronomers, yet their dedication allowed them to spend hours at modest telescopes or in front of computer screens, capturing additional data and checking the stars' behavior. Their participation blurred the line between expert and enthusiast, showing how curiosity and patience can open doors into cosmic discovery. The star, in turn, rewarded them with a puzzle that professionals and amateurs could share. As interest grew, astronomer Tabitha Boyajian and her colleagues decided to organize a sustained observing campaign to monitor the star. They turned to the public for help, launching a crowdfunding effort that raised more than $100,000. The funds paid for valuable telescope time at the Las Cumbres Observatory network, a distributed array that could watch the star almost continuously from multiple locations. Supporters not only donated money, but also became part of the story, following updates and cheering each new observation. Their enthusiasm was a reminder that, even in an era of advanced instruments, passion and community can drive exploration. The dedicated campaign soon bore fruit. Between March 2016 and the end of 2017, observers witnessed 4 significant dimming events, each with its own personality. These dips were not identical. They varied in depth and duration, and none repeated in a way that would suggest a stable orbiting object. To give them character, and to celebrate the community that made the observations possible, the team invited supporters to nominate and vote on names. The resulting names, Elsie, Celeste, Skara Brae, and Angkor, evoke ancient lost cities and hint at a sense of discovery tempered by mystery. The first of these events, Elsie, began in May 2017 and was caught by the Las Cumbres Observatory before spreading excitement across other telescopes. Observatories around the world quickly joined in, confirming that the star's light was fading by almost 2%. Messages flew across time zones as observers compared notes and adjusted their schedules to catch every moment of the dip. In a playful nod to the project's initials, LC for Las Cumbres and Light Curve, the dip was christened Elsie, a name that conjures an image of something familiar yet elusive. The shared effort underscored how the star inspired collaboration on a global scale. The pattern repeated through the summer and autumn. In July, a deeper dip called Celeste dimmed the star's light by 3%. A month later, another event named Skara Brae reached 2%. In September, a dip dubbed Angkor recorded a similar decline. Each name was chosen by the community, drawn from ancient settlements that vanished long ago. The sequence suggested a series of passing shadows, rather than a single orbiting companion, adding to the mystique. Supporters delighted in the names because they connected the star's behavior to stories of hidden worlds and bygone civilizations, reinforcing the idea that we were glimpsing something rare and fleeting. As data accumulated, scientists began to compare the star's dimming in different colors of light. They found that when the star faded, it dimmed less in the infrared than in the ultraviolet, meaning that shorter wavelengths were blocked more than longer ones. This was a crucial clue, because solid objects, whether planets or megastructures, would block all colors equally. The wavelength dependence pointed instead to a cloud of fine dust, with grains perhaps only a few micrometers across, absorbing and scattering blue light more effectively than red. Such dust could explain the differences in brightness without invoking opaque structures. To make sense of this, researchers turned to the physics of scattering. Very small particles can interact with light differently depending on its wavelength, a familiar effect that makes the sky appear blue and sunsets red. If the material around the star consisted of grains, just a few millionths of a meter in size, they could reduce the star's blue light more than its red, creating the observed color dependence. This idea suggested a ring or cloud of dust orbiting the star on a timescale of around 700 days, casting irregular shadows when denser clumps drifted across our line of sight. The explanation was mundane yet elegant, demonstrating how tiny particles can produce profound effects. By mid-2017, a consensus was emerging that an uneven cloud of dust could account for the star's gradual fading over months and years. This conclusion was important because it undermined the more exotic hypotheses, including the notion of a colossal artificial structure. The Spitzer and Swift telescopes provided further support by showing that the star's overall dimming was stronger at shorter wavelengths, just as the dust model predicted. Yet, as comforting as this explanation was, it did not fully resolve the short, deep dips that had captured the public's imagination. Even with dust in the picture, there remained something unexplained at the heart of the flicker. Some researchers suggested that clumps of comets could be responsible for the short dips. A swarm of icy bodies, perhaps perturbed from a distant orbit, might pass in front of the star and release dust as they disintegrated, creating irregular patterns of dimming. While this idea aligned with the unpredictable nature of the dips, it had trouble explaining how such swarms would persist, or why the dips were sometimes symmetrical. Others proposed that a large ringed planet, or even a brown dwarf with an entourage of debris, might transit the star. None of these scenarios fit all observations, keeping the mystery alive. Subsequent studies showed that the star's light faded differently across the spectrum, leading experts to dismiss the megastructure hypothesis in favor of dust. Yet the idea that something extraordinary might be hiding there had already captured the world's attention. Citizen scientists, inspired by this star, continued to scan the heavens, hoping to find other anomalies. The unpredictability of K1c 8462852 hinted that there might be more such objects waiting to be found. As telescopes improved and data streams grew, the partnership between professional astronomers and amateurs promised to reveal new secrets. When NASA launched the Kepler mission in 2009, its mandate was to watch a single region of the Milky Way with unwavering patience. The spacecraft's camera, fixed on more than 100,000 distant suns, measured their brightness minute by minute. By charting these light curves, scientists hoped to detect the telltale dips caused by planets crossing their stars. The method was straightforward, but the scale of the data was unprecedented. For 4 years, Kepler recorded subtle fluctuations, generating a deluge of numbers that would later be sifted for signs of hidden worlds. In most cases, a planet the size of Jupiter dims its star by about 1%, while Earth-sized worlds produce dips of only a fraction of a percent. These signals are periodic, repeating every time the planet completes its orbit. The reliability of such patterns allows astronomers to calculate planetary sizes and orbital periods with precision. Against this backdrop of orderly transits, a light curve plunging by 20% with no periodicity looked like a flashing sign that something different was happening. The depths of the dips alone were enough to make KIC 8462852 stand out. Because the Kepler dataset was so vast, algorithms were needed to sift through it, but computers can miss unusual signals. To complement automated searches, the Planet Hunters project invited thousands of volunteers to look at the light curves. Each volunteer saw graphs representing the brightness of stars over time and was asked to flag anything that seemed odd. People from many walks of life joined, devoting their spare hours to staring at wiggly lines on a screen. Their collective eyes often spotted patterns that software overlooked, and their enthusiasm created a new kind of astronomical workforce. The volunteers who discovered the star's unusual behavior were not celebrity scientists, but ordinary people, drawn together by curiosity. One might spend a day managing a factory floor, then come home and classify light curves. Another might oversee safety protocols at a company, yet still make time to check the brightness of stars after dinner. A third person, skilled in training workers, applied that same patience to training themselves to recognize subtle patterns in graphs. Their backgrounds varied, but they shared a love of discovery and a willingness to persevere through thousands of unremarkable plots to find the one that made their breath catch. Among the countless stars observed by Kepler, KYC 8462852 appeared unremarkable at first glance. It was only when volunteers noticed its wild fluctuations that the star was brought to professional attention. Once astronomer Tabitha Boyajian and her collaborators investigated, they gave the star a nickname, Boyajian's star, in recognition of her leadership in understanding it. Soon, the playful moniker Tabby's star also circulated, creating a sense of familiarity for an object thousands of light years away. These names anchored the star in the human story that was unfolding around it. The volunteers' commitment did not end with the initial discovery. When a longer observing campaign was proposed, they responded by funding it themselves. Through a crowdfunding effort, people who had never met each other pooled their resources to pay for telescope time. They understood that continuous monitoring was essential to catch the star's unpredictable dimming events, and their donations made it possible. In return, they received updates, access to data, and the satisfaction of knowing that they were directly supporting science. The project blurred the lines between observer and participant, creating a community united by wonder. When the first new dimming event occurred after the crowd-funded campaign began, it felt like catching a meteor at the moment it streaked across the sky. In May 2017, the team noticed a decline of nearly 2% and quickly alerted observers around the world. The rapid sharing of information allowed telescopes in different hemispheres to pick up where others left off, ensuring continuous coverage as Earth's rotation moved each observatory out of view. The excitement was palpable. Messages containing graphs and commentary flew across email lists and social media, turning the monitoring into a shared vigil. After each dimming event was recorded, supporters were invited to suggest and vote on names. The act of naming served both practical and symbolic purposes. It made it easier to refer to the dips in papers and discussions, and it allowed the community to leave a mark on the research. Names like Elsie, Celeste, Skara Brae, and Angkor were drawn from ancient settlements whose histories are full of mysteries and discoveries. By invoking lost cities, the names hinted at the hidden nature of the phenomena and the sense that the star's past might be as complex as our own. The creative process of choosing names drew more people into the narrative. KYC 8462852. Classification: as an F-type main sequence star with a red dwarf companion, places it in a familiar family of stars. Yet its behavior was anything but ordinary. Binary systems are common in the galaxy, and the gravitational interactions between stars can influence the orbits of surrounding material. It is possible that the companion star perturbs clouds of dust or comets, sending them across our line of sight. The physical properties of the primary star, including its temperature and luminosity, set the stage for the interplay of light and shadow. Understanding the star's environment is crucial to deciphering its unusual light curve. Many volunteers were curious about the scientific explanations emerging from the data. The concept of wavelength-dependent scattering, for instance, may seem abstract, but has analogies in everyday life. Sunlight scattering off molecules in Earth's atmosphere makes the sky blue. Similarly, dust around the star can scatter blue light more than red. When we apply this understanding to Tabby's star, we imagine a cloud of tiny particles swirling around it, causing the star to appear slightly redder when it dims. Such insights help demystify the observations without diminishing the wonder they inspire. For professional astronomers, arriving at a plausible physical explanation was both a relief and a reminder that nature is full of surprises. By studying the wavelength dependence of the star's brightness changes, they concluded that dust was the most likely cause of its long-term fading. This result dashed the hopes of those who wished for evidence of alien engineering, but replaced them with questions about the origin and evolution of circumstellar dust. It showed that even a dusty ring can mimic the effects of something exotic, challenging researchers to refine their interpretations. Even after the dust model gained support, puzzles remained. The short, sharp dips did not appear to be explained by the same mechanism. The comet swarm hypothesis offered one possibility. Perhaps a long-period companion star had disturbed a family of icy bodies, causing them to fall inward and evaporate as they passed in front of the star. The release of gas and dust could produce irregular, asymmetric dips. But there were challenges to this idea, including the sheer number of comets required and the stability of their orbits. Each answer led to new questions. While the notion of a giant artificial construct may have faded, the star remains central to conversations about the search for life beyond Earth. Its extreme behavior underscores how little we know about the diversity of stellar phenomena. In lectures and articles, scientists still use Tabby's star as an example of how we might detect technology if it exists, because unusual light curves were once proposed as a potential signature. At the same time, the star's story illustrates how extraordinary claims require extraordinary evidence, and how careful analysis can reveal simple causes behind striking effects. The tale educates and inspires simultaneously. As the investigation continued, the relationships formed through the Planet Hunters project deepened. Volunteers swapped tips on reading light curves, while professional astronomers shared insights into data analysis. Web forums buzzed with discussion, and people who had never thought of themselves as scientists found themselves debating the significance of a 0.5% dip in brightness. Teachers used the star's story in classrooms to show students that discovery is not limited to professionals. For many, the experience turned an abstract appreciation for the cosmos into a personal engagement with the process of science. By the time the first research papers on KYC 846-2852 were published, the star had become a symbol of the unexpected. What began as a volunteer spotting an anomalous light curve grew into a worldwide collaboration, supported by public funding, professional resources, and international coordination. The story of its discovery highlighted the power of open data and the value of eyes and minds from beyond academia. The initial observations were only the beginning. Many realized that the next steps would require even more sustained attention. The stage was set for deeper involvement, both from those who had already joined and from new participants intrigued by the enigma. One of the most charming aspects of the story was learning who the observers were. The seatbelt factory foreman, who became an amateur astronomer, used his experience with precision manufacturing to calibrate his equipment. The security coordinator, who normally ensured safety for employees, found solace in aligning telescopes under the night sky. The trainer, who taught others to master machinery, applied the same patience to mastering light curves. Each brought unique skills, and together they contributed to data that would have been difficult to gather without them. Their experiences demonstrated that serendipity often favors those who are willing to try something new. In the early days of Planet Hunters, most volunteers saw endless streams of ordinary light curves. It was therefore a stroke of luck that a few of them happened to be assigned the data for KIC 8462852. They saw the star's brightness plunge and felt a jolt of excitement, unsure whether they were witnessing an error or a genuine anomaly. Their willingness to flag the curve, combined with the platform's system of cross-checking by multiple volunteers, ensured that the pattern was noticed. Serendipity, in this case, was not blind chance, but chance combined with attentive eyes. When the team turned to crowdfunding, supporters responded because they already felt invested. Their initial discovery had sparked a bond with the star, and funding more observations allowed them to continue following its story. Many backers wrote comments about how they had never donated to scientific research before, but felt compelled to contribute because this project belonged to everyone. The campaign succeeded quickly, showing that when people are invited into the process of science, they are willing to support it materially. The sense of shared ownership was itself a reward, making each new observation feel like a collective achievement. Observing a dip in real time required an international network of observers. As the star's brightness began to fall, astronomers and amateurs across continents coordinated their schedules. People in Spain handed off to observers in the United States, who then passed the baton to colleagues in Australia or South Africa. The global chain of observations allowed coverage around the clock, an advantage that professional observatories alone could not provide. The collaboration felt like a relay race, with each observer contributing a segment to the complete light curve. Serendipity depended on planning and cooperation, and the thrill of catching a dip was amplified by the knowledge that others were watching with you. The naming of the dips became a beloved tradition. Supporters submitted suggestions drawn from mythology, literature, and geography, and then voted on their favourites. The winning names often had layers of meaning. Celeste evokes the heavens. Skara Brae is an ancient stone settlement buried for centuries under sand. And Angkor is a once-forgotten city, surrounded by jungle. By attaching these names to fleeting, dimming events, the community created narrative threads that connected the star's behaviour to human history. The process added a layer of storytelling to the science, reminding everyone that we interpret data through the lens of our own culture. As the observing campaign continued, the unpredictable nature of the star's fluctuations kept participants on their toes. One astrophysicist described the star as the most unusual object in the galaxy, and that description became a rallying cry for observers hoping to catch the next dip. People would check nightly updates, hoping to see a small decline that might signal an impending event. The erratic timing meant there were stretches of weeks or months with nothing to report, followed by a sudden plunge that demanded immediate attention. The unpredictability added to the allure, making every observation feel like a potential discovery. The volunteers were well aware of the various theories proposed to explain the star. Some were amused by the early speculation about alien megastructures and enjoyed the headlines that followed, even if they knew the idea was unlikely. Others were intrigued by the possibility of comet swarms or dust clouds and sought to understand the science behind them. When the Spitzer and Swift telescopes provided evidence for dust, many volunteers felt a mix of satisfaction and disappointment. Satisfaction because a plausible explanation had been found, and disappointment because the mystery felt less exotic. Their emotional journey mirrored that of the wider public. As they followed updates, volunteers also became learners. They read about how light of different wavelengths interacts with matter, discovering terms like Rayleigh scattering and extinction. Discussions on forums sometimes delved into the physics of small particles and how they could cause the observed colour dependence. People who had never studied astronomy found themselves drawing diagrams and using simple equations to model dust clouds. The project became not only a quest for data, but also an education in astrophysics. Learning the underlying science deepened their appreciation, turning a seemingly obscure star into a teacher. In parallel with the dust hypothesis, enthusiasts entertained a variety of other ideas. Perhaps, some thought, a debris disk left over from planet formation might be responsible. Others considered the notion that a giant planet with rings could produce irregular dips, like Saturn on a cosmic scale. There were speculative discussions about a planet being torn apart and consumed by the star, leaving behind a trail of debris. While none of these explanations fully matched the data, The process of debating them fostered a culture of open inquiry. Volunteers learned to weigh evidence, compare models, and appreciate the complexity of interpreting astronomical observations. The comet swarm hypothesis remained a favorite among some community members because it allowed for multiple objects and variable depths. People created simple models to see how groups of comets could produce the observed dips. They considered scenarios in which a large body disrupted a cloud of smaller objects, sending them spiraling inward. They plotted the durations of the dips against the depth and tried to match them to hypothetical comet sizes. Although there were challenges with this model, the exercise of modeling possibilities gave volunteers hands-on experience with scientific reasoning. They came to understand the constraints that make some theories more plausible than others. The multi-wavelength observations remained central to the debate because they provided a direct test of competing hypotheses. If large opaque objects were causing the dips, the dimming would be equal across all colors. Instead, the data showed that the star dimmed more at shorter wavelengths, strongly suggesting that tiny dust grains were responsible. Volunteers repeated this point to newcomers on forums, summarizing the evidence in plain language. They took pride in explaining why the dust model fit better than any scenario involving solid bodies. Their ability to communicate complex ideas clearly was one of the community's strengths. Each of the 4 dips observed during the 2016 to 2017 campaign became a milestone for the community. People remembered where they were when Elsie began, just as others recall where they were when they saw a comet. Celeste and Skara Bray brought people back to their screens during the height of summer, while Anchor took place amid autumn leaves. After each event, volunteers analysed the depth and shape of the dip, comparing them to previous ones and trying to guess what might come next. The anticipation built a sense of continuity and kept the community engaged, even during long, quiet periods. When research papers finally concluded that dust was the most likely cause, many volunteers accepted the result with grace. They noted that the wavelength dependence was a strong argument, and that extraordinary claims require robust evidence. The shift did not dampen their interest. Instead, it redirected it toward understanding the dust's origin and evolution. Questions about the formation of the dust cloud, its stability, and its relationship to the companion star became new threads of discussion. The star remained fascinating, even without aliens, proving that the universe is rich with mysteries that do not need external intelligence to be intriguing. The campaign also changed the volunteers' daily routines. Some adjusted their sleep schedules to monitor the star when it was visible in their time zone. Others set up alerts to notify them of any changes in brightness, so they could take quick measurements. The act of participating brought them outside at odd hours, giving them time to gaze at the night sky and feel connected to the cosmos. Even those who did not have telescopes felt engaged by watching the data stream. The star became part of their lives, reminding them that science can be both communal and intensely personal. By the end of the first phase of observations, the story of Tabby's star had become a testament to the power of citizen science and serendipity. A chance assignment of data to volunteers led to the discovery of the most unusual light curve in Kepler's archive. A crowd-funded campaign enabled sustained observations that captured 4 distinct dimming events. A network of amateur and professional astronomers worked together across time zones, sharing the thrill of each dip. The star united people who might never have met, fostering a community built on curiosity, cooperation, and a shared love of mystery. The first dip of the 2017 campaign, nicknamed Elsie, lasted several days and reached a depth of nearly 2%. When graphed, the dip exhibited an asymmetric shape, a relatively steep descent, a shallow minimum, and a gradual recovery. Some observers likened its outline to a whale's back, with a gentle slope on one side and a steeper cliff on the other. The shape suggested that whatever was blocking the star's light was not a simple, uniform object, but something with structure or an uneven distribution of material. The details of this curve provided clues for theorists and a striking visual for everyone following along. The subsequent dips each had their own personality. Celeste was deeper, reaching a 3% drop, and its light curve showed a more symmetrical profile, with a smooth decline and recovery. Skara Brae, by contrast, was shallower and shorter, suggesting a smaller or less dense structure passing in front of the star. Angkor fell somewhere in between, with a 2% dip and hints of substructure within the overall decline. The differences reminded observers that they were not dealing with a single repeating transit, but with a series of distinct events, each potentially caused by different clumps of material. Naming the dips after lost cities proved to be an apt metaphor. Just as those ancient settlements are known through ruins and stories, the dips were glimpsed through traces on a graph. The star's light curve became a map where mysterious features were labelled with evocative names, inviting speculation about what lay behind them. The idea of lost cities also resonated with the notion that the events we observed had occurred hundreds of years ago, since light from the star takes that long to reach us. Each name, therefore, conjured both the distance and the depth of the mystery. The shapes of the dips suggested that we might be seeing different kinds of objects or configurations at each pass. A cometary fragment with an extended tail could produce an asymmetric dip, while a more compact cloud might generate a symmetric one. Alternatively, the dips could be caused by different concentrations within a larger dust ring, with denser clumps producing deeper declines. Modelling these possibilities required assumptions about the size, composition, and velocity of the material. Each model could be tested against the observed light curves, but the variety of shapes meant there was likely more than one mechanism at play. Multi-wavelength observations of the dips added an additional dimension to the analysis. For each event, astronomers measured how the star's brightness changed in different filters. They found that, in general, the dips were deeper in blue light than in red, reinforcing the idea of small particles causing the obscuration. However, the exact degree of color dependence varied between dips, suggesting differences in particle size or composition. These variations hinted that the material was not homogeneous. Instead, the star might be surrounded by a mixture of grain sizes, with some clumps containing finer dust and others containing slightly larger particles. The irregular shadow became more intricate the closer we looked. The physics of scattering provides a beautiful explanation for why dust with different particle sizes can produce different color signatures. Smaller grains preferentially scatter shorter wavelengths, making the star appear redder when they pass in front. Larger grains scatter more evenly, leading to dips that affect all colors similarly. Observers found that some dips showed a strong color dependence, while others did not, implying a range of grain sizes. The interplay of light and matter around the star thus resembled the interplay of sunlight and clouds on Earth. Just as no two sunsets are exactly alike, no two dips were identical. While dust seemed to account for the star's long-term dimming, the irregular dips remained partly mysterious. The overall brightness of the star has been fading gradually over the past decade, and this trend is best explained by a cloud of dust orbiting with a period of roughly 700 days. However, the short-term dips are superimposed on this fade, and their depths and timings do not match a single orbital period. The combination of a steady fade and sporadic dips implies a complex environment, perhaps involving both a persistent dust ring and transient clouds or bodies. The presence of a red dwarf companion adds another layer of complexity. In binary systems, gravitational interactions can perturb the orbits of circumstellar material. If the companion star periodically swings close to the primary, it could disturb a reservoir of comets or dust, sending material inward. Alternatively, gravitational resonances could shepherd dust into clumps that align with certain orbits. These dynamics are difficult to model without precise knowledge of the companion's orbit, but they illustrate how even a small secondary star can influence the environment of a larger primary. The irregular shadow may thus result from a dance between two stars and their debris. The irregular shadow also revived interest in exotic possibilities. Some proposed that a giant planet with an enormous ring system, perhaps many times larger than Saturn's, could orbit the star on a tilted path. As the rings crossed our line of sight, they could produce dips of varying depths and durations. Others wondered whether we were witnessing the aftermath of a planetary collision, or the consumption of a planet by the star, events that could fill the system with debris. Such scenarios were difficult to prove, but served as reminders that stars can host complex and sometimes violent histories. Modelling the irregular dips required blending astrophysics with creativity. Researchers had to imagine structures that could survive in the harsh environment around a star and produce the observed light curves. They ran simulations of swarms of bodies, rings with gaps, and dust clouds of varying densities. Each simulation produced a light curve that could be compared to observations, but none matched perfectly. This process highlighted the limits of current models and the need for more data. The star seemed to be telling us that our understanding of circumstellar environments was incomplete. Observations across multiple wavelengths became crucial tools for narrowing down possibilities. By simultaneously monitoring the star in ultraviolet, visible, and infrared light, astronomers could separate dust effects from those of larger bodies. Infrared observations are particularly sensitive to warm dust, while ultraviolet data can reveal scattering by very small grains. Combining these data sets allowed researchers to build a more complete picture of the star's environment. The irregular shadow resolved differently in each band, like a sculpture viewed under changing light. The multi-wavelength approach demonstrated how variety in data leads to clarity in interpretation. Gathering data in different colors also required coordination among observatories with diverse capabilities. Amateur astronomers at Astrolab and other small telescopes often collected visible light measurements, while space-based observatories like Spitzer and Swift contributed infrared and ultraviolet data. The volunteers' observations were critical because they provided continuous coverage that larger instruments could not maintain. Their work allowed researchers to align ground-based and space-based datasets, ensuring that no part of a dip was missed. This synergy between small and large telescopes showcased the value of a distributed observing network. During each dip, the observing network functioned like a well-coordinated orchestra. As soon as a decline was detected, messages went out to schedule observations in multiple bands. Observatories with spectrographs took spectra to see if any new absorption features appeared, while photometric instruments recorded precise brightness measurements. Some observers experimented with polarimetry to detect dust scattering. The choreography required rapid communication and flexibility because the dips could arrive without warning. Yet the network responded smoothly, reflecting the experience gained from previous events. The irregular shadow became an exercise in collective responsiveness. Beyond the specific mystery, the irregular shadow offered lessons for future surveys. It showed that anomalies can remain hidden in datasets until human eyes find them, emphasizing the value of citizen participation. It highlighted the need for continuous, multi-wavelength monitoring to understand transient events, and it reminded scientists that the universe can surprise them with phenomena that fall outside current classification schemes. The knowledge gained from Tabby's star influenced how new missions plan to detect and follow up on irregular signals. The shadow was a teacher as well as a puzzle. By the end of several years of observing, the irregular shadow had evolved from a simple curiosity to a complex phenomenon that blended physics with storytelling. Each dip had a name and a personality. Each color curve hinted at the composition of unseen material, and each theory sparked debate and further investigation. The star taught us to look carefully, to question assumptions, and to appreciate the richness of celestial dynamics. Yet many questions remained unanswered, setting the stage for the exploration of deeper possibilities and early theories that had arisen before the dust settled. The first reaction to the star's bizarre light curve was to suspect a malfunction. Kepler's detectors occasionally produced artifacts, and data pipelines sometimes introduced noise. Researchers checked calibration files, compared different processing methods, and looked for similar patterns in other stars. When the dips persisted across independent reductions and in data from other telescopes, the instrument error hypothesis was largely ruled out. This process illustrated how skepticism is the starting point of investigation. Only when the mundane causes are excluded do scientists turn to more exotic possibilities. Because Kepler's mission was to find planets, the first natural explanation was that one or more large planets with complex ring systems could cause the dips. Ringed planets can produce unusual light curves if the rings are tilted or have gaps. Yet planetary transits are periodic, repeating every orbit, and none of the dips matched a consistent period. Models of ringed planets also predicted specific shapes and durations that did not fit the data. As appealing as the idea was, the planet explanation faded as evidence accumulated. It became clear that if planets were involved, they were not alone. Some researchers considered that the star might be surrounded by a debris disk from a recent collision. If two large bodies had smashed together, the resulting cloud of dust and fragments could produce irregular dips as its orbit slowly dispersed. Others proposed that the star might be consuming a planet, tearing it apart, and gradually accreting its material. This process could feed a disk or ring that would periodically block the star's light. Another suggestion was that we were witnessing a younger star with material still coalescing around it. Though Tabby's star did not fit the typical profile of such youth. Each scenario had strengths and weaknesses, and none matched all observations. The comet swarm hypothesis gained attention because comets are known to produce variable, asymmetric transits. A family of comets perturbed by a passing star or planet could cross in front of Tabby's star, each leaving behind a tail of dust. This scenario could account for multiple dips with different depths and durations. However, calculations showed that hundreds of large comets would be required to produce the observed amount of dimming, and the likelihood of such a swarm existing in just the right orientation was low. While attractive for its connection to known solar system phenomena, the comet explanation struggled with its improbability. The dust ring hypothesis offered a simple explanation that matched the color dependence of the dips. A ring of dust with clumps of varying density could produce both the long-term fading and the irregular short dips. Tiny grains scatter blue light, making the star appear redder when it dims, consistent with observations. However, maintaining such a ring around a star requires a source of replenishment, as small particles are quickly blown away by radiation pressure. What could be feeding the dust? Comets or asteroids being ground down, perhaps, or collisions among debris. The dust model solved one puzzle while introducing another. Multi-wavelength data strengthened the case for dust by showing that the dimming was greater in ultraviolet than in infrared, consistent with small grains. The size of the particles was estimated to be a few micrometers, about the width of human hairs. Such particles can form from the grinding of larger bodies or the outgassing of comets. The pattern of scattering provided a diagnostic tool, allowing scientists to compare their models to observations. The dust explanation moved from speculation to evidence-based theory as more data were gathered. Yet the source and longevity of the dust remained open questions. Recognizing that no single model fully explained the data, some scientists proposed hybrid scenarios. In these, comets or asteroids passing near the star shed dust, feeding a circumstellar cloud. Periodic disturbances from the companion star could send waves through the dust, causing it to clump and disperse. The combination of large bodies and fine particles could produce a wide range of light curve shapes. Such hybrid models offered flexibility, but were difficult to test directly. They captured the idea that a simple, singular cause might not exist. Instead, the star's behavior could result from multiple processes interacting. The initial theories also included more unusual configurations, such as a large planet accompanied by a swarm of Trojan asteroids. These Trojans could orbit at stable points ahead of and behind the planet, creating a train of objects that would cross the star at irregular intervals. Another idea was that we were witnessing a planetary debris field from the breakup of a moon or dwarf planet. Still others speculated that we were seeing material left over from the star's formation, preserved because of its companion's gravitational influence. Each scenario provoked debate and stimulated new research directions. Amid the scientific explanations, the idea of an alien megastructure captured public imagination. If a civilization were harvesting energy from its star with vast solar collectors, the passing structures could cause irregular dips. The concept was not invented for this star. It had been proposed decades earlier as a potential signature of advanced technology. In the absence of a natural explanation, the media speculated wildly about alien spheres, though scientists cautioned that such claims were premature. When multi-wavelength observations indicated that dust was responsible, the megastructure idea lost support. Nevertheless, the star became an example of how searching for anomalies can intersect with the search for life. Even after the dust explanation prevailed, the star continued to appear in talks about searching for extraterrestrial life. Astrophysicists used it to illustrate how one might identify artificial structures by their impact on starlight. They cautioned, however, that natural phenomena can mimic the signatures we might attribute to technology. The lesson was that extraordinary claims require extraordinary evidence, and that curiosity should be tempered with skepticism. The star's irregular light curve thus became a teaching tool, reminding audiences that the universe can be surprising without invoking aliens. The dust explanation eventually became the leading theory because it was both physically plausible and consistent with the data. The scattering of light by small particles is a well-understood phenomenon that occurs in many contexts. By applying this understanding to Tabby's star, scientists could account for the color dependence and the gradual fading. The elegance of the solution lay in its simplicity. No need for massive structures or exotic physics, just a cloud of tiny grains orbiting a star. At the same time, the model left room for additional complexity, acknowledging that dust alone might not explain every feature. With dust as the baseline explanation, researchers turned to secondary questions. Where did the dust come from, and how was it replenished? How did the companion star influence the dust's distribution? Could collisions among asteroids produce enough material, or were comets the main source? Long-term monitoring and modeling aimed to answer these questions. The star became a laboratory for studying circumstellar dust dynamics, a topic relevant not only for understanding anomalies, but also for interpreting observations of other stars. The initial theories thus evolved into a research program. Throughout the development of these theories, volunteers remained engaged. On discussion boards, they debated the merits of each hypothesis, weighing evidence and reasoning through the implications. They read academic papers, asked questions, and sometimes spotted inconsistencies or overlooked details. Their participation added a layer of peer review and helped disseminate information in accessible language. The process of eliminating theories became a collective exercise in scientific thinking. For many, it was the first time they had engaged so deeply with the process of hypothesis and test. The star's mystery thus served as a classroom for the scientific method. As more data came in, the narrative of the star changed. The initial rumors of aliens subsided, replaced by careful analyses of wavelength-dependent dimming. Press releases emphasized the dust explanation, but they also acknowledged that not all aspects were resolved. Journalists who had once speculated about megastructures now wrote about the beauty of scattering and the importance of citizen science. The star's story became a case study in how science progresses through observation, hypothesis, testing, and revision. The fact that the conclusion was less sensational than some hoped did not make it less profound. In the end, the initial theories about Tabby's star ranged from mundane to extraordinary. Each was considered, debated, and either refined or discarded based on emerging evidence. The process highlighted the creativity and rigor of the scientific community and the value of engaging the public in speculation grounded in data. By exploring comets, dust, planets, collisions, and even megastructures, scientists and volunteers expanded their understanding of what might occur around distant stars. The journey through these ideas enriched the narrative and left participants ready for the next phase, contemplating why such a puzzle captured imaginations so deeply. There is something inherently captivating about a light that flickers without warning in the dark. Tabby's star taps into a deep human response to irregular glimmers, the same fascination that makes people watch fireflies or campfires. When astronomers describe it as the strangest star in the galaxy, they are not only stating a fact, but also invoking a feeling. The unpredictability invites us to imagine forces at work that we do not yet understand. It whispers that there are corners of the universe where the familiar rules may play out in unfamiliar ways. The spark of wonder was not limited to professional astronomers. People who had never owned a telescope found themselves checking updates on the star's brightness before bed. Supporters spoke of feeling connected to something larger than themselves, of the thrill of participating in a discovery that spanned continents. The collective anticipation before each observing season and the communal sighs when a dip occurred fostered a shared emotional landscape. Wonder became communal rather than solitary, a thread that tied together individuals who might otherwise never have met. Giving names to the dips transformed data into stories. Just as characters in a novel help readers connect with a narrative, Elsie, Celeste, Skara Brae, and Angkor helped people remember and care about specific events. The names evoked lost cities, adding layers of symbolism and inviting speculation about what lay unseen around the star. They also served as markers in time, like chapter headings in a book. Each name spurred new discussions, artwork, and even poems. The act of naming turned the star's behavior into a saga, with episodes that could be recounted and shared. Some feared that a prosaic explanation would rob the star of its magic, but the opposite occurred. Learning about scattering and dust made the phenomenon more, not less, awe-inspiring. Visualizing microscopic grains dancing in orbit, casting shadows across light that had traveled for centuries, is poetic in its own right. The fact that such tiny particles could mimic the signatures of vast structures highlights the subtlety of nature. Understanding deepened appreciation, showing that knowledge and wonder are not adversaries, but partners. The story also demonstrates that curiosity is not confined to a particular profession or background. The seatbelt factory foreman, the security coordinator, and the trainer found in the star a common interest that transcended their daily jobs. Their participation sent a message that anyone can contribute to scientific discovery if they are given the opportunity and the tools. Wonder thus became a bridge, connecting diverse individuals in a shared quest. It challenged the notion of science as an exclusive domain and celebrated it as a human endeavor open to all. Even with dust as the leading explanation, many questions remain. What events gave rise to the dust? And how is it sustained? Are we witnessing a transient phase in the star's life, or a long-standing pattern? The answers could involve collisions, evaporation, or gravitational interactions. Contemplating these possibilities keeps the mind engaged and the sense of wonder alive. The star teaches that answers often lead to deeper questions, and that mystery can coexist with understanding. Speculations about giant ringed planets, comet swarms, planetary consumption, and even artificial structures may have been incorrect, but they sparked creativity. Imagining enormous ring systems or fleets of comets forced people to stretch their minds beyond everyday experience. Even the alien megastructure idea, though unsupported, encouraged discussions about how we might detect signs of life elsewhere. Through this star, people practiced a kind of cosmic thought experiment, exploring the limits of the plausible and the boundary between science and science fiction. The spark of wonder illuminated possibilities beyond the immediate answer. The light we see from Tabby's star began its journey more than 14 centuries ago, long before telescopes existed. When we observe a dip, we are seeing a shadow cast hundreds of years in the past. This temporal distance adds a layer of poignancy to the wonder. We cannot change what happened around that star. We can only witness it long after the fact. The sense of looking back in time, across an abyss of space, reminds us of the vast scale of the universe and our small but meaningful ability to perceive it. The success of the crowdfunding campaign represents a shift in how science can engage the public. Instead of simply reading about discoveries after the fact, people contributed directly to the process. They chose to invest in a question that had no guarantee of a dramatic answer, because they valued the act of asking. This model of participation transforms wonder from passive admiration into active support. It demonstrates that people are willing to fund the pursuit of knowledge for its own sake, and that they find joy in being part of something bigger. Through forums, mailing lists, and social media, a community formed around the star. People shared not only data, but also their feelings of anticipation and excitement. They celebrated successes and commiserated when a dip ended sooner than hoped. Friendships formed among individuals who had never met in person, united by a flickering point of light in the sky. The star fostered a sense of belonging, showing that wonder can be a social glue. It turned isolated stargazing into a collective experience. Teachers and science communicators found in Tabby's star a gateway to explain astrophysics. Lessons on light scattering, stellar evolution, and exoplanet detection could be anchored in the star's behavior. Students who might have been intimidated by equations were drawn in by the mystery and stayed for the science. Visualizing the dips and connecting them to real phenomena made abstract concepts tangible. In this way, the spark of wonder ignited a flame of learning, inspiring a new generation of learners to explore the cosmos. Part of what made each dip so captivating was its fleeting nature. They came without warning and were over in days or weeks. Missing a dip meant waiting indefinitely for the next. creating a sense of urgency that heightened excitement. Observers stayed alert, knowing that each event was unique and might never repeat. The transient quality reminded participants that many wonders of the universe are impermanent, and that appreciating them requires attention. The star taught patience and vigilance, and the moments of dimming felt like gifts. Throughout the investigation, a delicate balance existed between imagination and evidence. People allowed themselves to consider extraordinary possibilities while remaining grounded in what the data could support. This balance kept wonder alive without succumbing to fanciful speculation. It encouraged creativity in modelling and caution in interpretation. In the dance between dreaming and knowing, the star's mystery unfolded. The tension between what might be and what is created a space where curiosity could thrive. The legacy of Tabby's star extends beyond the specifics of dust or comets. It has influenced how astronomers approach unexpected data, highlighting the value of openness to unusual possibilities. It has reinforced the importance of collaboration between professionals and citizen scientists, and the need for multi-wavelength monitoring. It has shown that inviting public participation enriches both science and society. Future surveys will undoubtedly encounter anomalies, and the response to Tabby's star provides a template. Be curious, be thorough, and be inclusive. Wonder is a renewable resource when cultivated thoughtfully. In the end, Tabby's star remains a beacon of curiosity, shining from a distance of nearly 1,500 light-years. It reminds us that even common-type stars can surprise us, that the universe is still full of mysteries to explore, and that discovery is an ongoing process. The flicker in the dark continues, and with every new observation, the story deepens. We are left waiting for the next unexpected dip, the next clue that will refine our understanding. This anticipation carries us forward, linking the wonder of today to the discoveries of tomorrow, and gently inviting us into the next chapter. The memory of our star's mysterious flickers still lingers as we move into the next part of our story. Those gentle dips in brightness that captured the world's imagination are not random points in darkness. They are the beginnings of a conversation between us and a distant sun. To understand that conversation, scientists turn the star's flickers into a language of time and light. This language takes shape as a light curve, a simple graph that traces how the star's brightness rises and falls. When we speak of light curves, we imagine an astronomer sitting in the dark with a notebook, recording each sparkle as if it were a heartbeat. In reality, a computer does the watching, but the feeling is the same. An awareness of rhythm, of patterns that might reveal hidden companions. Each point on that curve is a measurement of light collected through a telescope's eye, calibrated and cleaned until it becomes data. Over time, those points form a continuous story, a whisper from a star billions of kilometers away. A light curve seems simple enough. Brightness on the vertical axis, time on the horizontal. Yet every wiggle and dip has meaning. When a planet crosses its star, the planet hides a tiny fraction of the star's light, and the light curve dips like a pulse beneath the baseline. The size of that dip, how quickly it fades and returns, reveals the size and orbit of the unseen world. During a typical planetary transit, the light curve exhibits a smooth, symmetrical shape. It begins with a gentle decline as the planet starts to cross, reaches a flat bottom when the planet is fully in front of the star, and then rises in a mirror image as the planet moves away. This pattern repeats every orbit with near-perfect regularity. For large gas giants close to their stars, the dip might be just a few % of the total light. For Earth-sized planets, it can be less than 0.1%. Such precision is a triumph of patience and technology. The Kepler Space Telescope, for example, stared at a patch of sky for years, measuring the brightness of more than 100,000 stars. It recorded data every 30 minutes, building curves that let scientists find planets smaller than Earth and map their orbits. Because Kepler watched continuously, it could distinguish between a real dip and the flicker of random noise. Light curves are delicate to interpret, because stars themselves are not static candles. They pulse, flare, and spot, sending out bursts and waves that add texture to the baseline. Solar flares and star spots can produce their own fluctuations, sometimes larger than a small planet's shadow. Astronomers must disentangle these intrinsic variations from the subtle signatures of orbiting bodies. In addition to transits, light curves can reveal eclipses in binary star systems, where two stars orbit each other and periodically pass in front of one another. Those curves show deeper and more complex patterns, with alternating dips corresponding to each star's contribution. Light curves also tell of pulsating stars that swell and contract like breathing organisms, their brightness waxing and waning on regular schedules. In each case, the curve is a record of movement and change. To understand the intricacies of Tabby's star, we must first appreciate the typical behavior captured in these curves. In a normal planetary system, the dips appear on a regular schedule, repeating with the orbital period. The depth of the dip is modest, often around 1% for a Jupiter-sized planet. The shape is smooth and symmetric, reflecting a simple, round object crossing a uniform disk of light. Even when multiple planets orbit a single star, their contributions to the light curve are like overlapping rhythms in a piece of music. Each planet's shadow appears at its own interval, adding a small dip that the eye can separate after careful analysis. Software can model these overlapping patterns to derive the number of planets, their sizes, and their orbital resonances. This is how we have come to know many of the exoplanetary systems discovered in recent years. Sometimes, transits can reveal more than the presence of a planet. As the light passes through the planet's atmosphere, certain wavelengths are absorbed, leaving faint fingerprints in the star's spectrum. By examining the light curve and spectrum together, scientists can infer the composition of alien skies, mapping clouds, hazes, and perhaps even the signs of life. These wonders are encoded in the smallest dips. The sensitivity required to detect such variations is extraordinary. For Earth around the Sun, the brightness drop is only about 0.008%. Noise from the instrument, the spacecraft's motion, and the star itself must be minimized to detect this tiny signal. Data processing pipelines remove trends and outliers to reveal the repeating pattern of transits. The result is a clean curve, a story of an unseen planet's dance. Light curves also help in understanding star spots and rotation. As a star rotates, dark spots on its surface come into and out of view, causing periodic modulations. By studying these modulations, astronomers can measure the star's rotation period and the distribution of spots, providing insight into stellar magnetism. Thus, a light curve is not only a tool for planet hunting, but a window into the star's own dynamics. In some cases, a star may host transiting exomoons. These produce subtle additional dips or timing variations in the transit of the planet, adding complexity to the light curve. Detecting such signals is extremely challenging, requiring precise measurements and long-term monitoring. Yet the possibility reminds us of the richness encoded in these simple graphs. When the brightness of a star changes due to circumstellar dust or debris, the light curve can look quite different. Dust often causes gradual dimming or irregular, asymmetric dips, depending on the distribution and size of the grains. Infrared observations help distinguish dust, as dust emits strongly at longer wavelengths. The shape and wavelength dependence of a dip are clues to the nature of the obscuring material. Scientists use modeling to compare observed light curves with theoretical ones. They simulate a star, a planet, or a cloud of dust and adjust parameters until the model matches the data. This process requires understanding of orbital mechanics, radiative transfer, and the interplay of light with matter. Each fit provides a possible explanation, but there can be many solutions, making interpretation as much art as science. Citizen scientists play an important role in light curve analysis. Projects like Planet Hunters invite the public to look at curves and identify unusual patterns that automated algorithms might miss. Human eyes can spot oddities and anomalies, just as they did in the case of Tabby's star. This collaboration between professionals and amateurs enriches the field and opens new avenues of discovery. It's easy to forget that behind every light curve is a living star, constantly fusing hydrogen, emitting energy, and moving through space. The curve is only a projection of that reality onto a graph. Our challenge is to interpret that projection, to reconstruct the three-dimensional story from a two-dimensional line. Each deviation holds a clue. Each return to baseline is a heartbeat. At a glance, a light curve looks like a seismogram, a record of earthquakes encoded as wiggles on paper. Astronomers study it in a similar way, looking for periodic signatures and sudden anomalies. They draw on statistics and physics to separate the signal from noise. In the case of Tabby's star, the anomalies soon prove to be unlike anything seen before. Understanding the typical shapes in light curves sets the stage for appreciating the strange case of KYC 8462852. When astronomers first saw its data, their training led them to search for periodic patterns, to look for the telltale symmetry of a transiting planet. But the curves refused to conform. They displayed dips of different depths, durations, and intervals, as if the star were engaged in a different kind of dance. Even before we delve into those peculiarities, it's important to remember that light curves are always a conversation between measurement and interpretation. The data must be trustworthy, cleaned of instrumental artifacts and cosmic rays. Once that foundation is secure, the challenge is to match the patterns to physical scenarios. In the case of Tabby's star, the list of possible scenarios quickly grew long and strange. When we read a light curve, we are reading time itself. Each dip marks a moment when something passed before the star, or when the star itself changed. The horizontal axis ticks forward relentlessly, capturing seasons and years. In the light curve of Tabby's star, we see a sequence of events stretched over many years, each one a puzzle piece in a cosmic mystery. Light curves also remind us of the finite nature of observation. Kepler observed Tabby's star for 4 years, capturing only a fraction of its long story. Ground-based telescopes have continued the monitoring, but clouds and day-night cycles limit what they can see. Our knowledge is shaped by these windows of attention, by what we have time to watch. Despite these limitations, light curves remain our best tool for probing distant systems. They can reveal not only planets, but rings, moons, dust clouds, and even hints of artificial structures, if such things exist. By mastering their interpretation, we prepare ourselves to tackle the unexpected. And when the unexpected appears, as it did with Tabby's star, we are reminded that the universe still has the power to surprise. This sense of surprise is part of the allure. Each light curve is a potential story, a chance to discover something no one has seen before. The simple act of plotting brightness against time becomes a detective work, an invitation to imagine hidden worlds and unseen events. In the following chapters, we will see how the light curve of one particular star led to some of the most imaginative hypotheses in modern astronomy. Before we leave this exploration of light curves, it's worth noting that they are more than just lines. They represent trust in the instruments, in the calibrations, in the assumptions we make about how light travels and how stars behave. In the case of Tabby's star, they required us to question those assumptions. The unusual dips forced us to consider whether our understanding of light and matter was missing something. This introspective aspect of science is often overlooked. We think of data as a window to truth, but data is always filtered through human perception and technology. Light curves are the product of algorithms that subtract trends and fill gaps. When something unusual appears, it prompts a re-evaluation of every step in the process. Was the instrument stable? Was the pipeline robust? For Tabby's star, such checks were done again and again. After these checks, the dips remained. They were not errors or cosmic rays. They were consistent features in the star's light curve, present in multiple data sets. To some, they appeared like beacons, signaling a phenomenon we did not yet understand. In the next chapter, we will contrast these dips with the expectations formed by typical planetary systems. The story of light curves is a story of patience, of staring into darkness and listening for whispers. It reminds us that the cosmos speaks in light, and that by tracing its fluctuations, we can infer the presence of worlds and phenomena we cannot see directly. With that foundation laid, we are ready to consider what happens when a light curve defies expectations. And so we begin the journey beyond the ordinary, carrying with us the knowledge of how light curves should behave. We will now explore a star whose light curve behaves like no other. A star whose flickers have inspired tales of comets, clouds, and even megastructures. The curves will guide us as we navigate this flickering mystery. Tabby's star, designated KYC 8462852, is by many measures an ordinary object. It is an F-type main sequence star, slightly hotter and more massive than our Sun, burning hydrogen in a steady rhythm. Yet its light curve is extraordinary. When astronomers first examined it, they saw something that defied the expectations built from thousands of planet-finding curves. The first hint came as a series of dips captured by Kepler in 2011. The star's brightness decreased by nearly 15%, a staggering amount when compared to the 1% dip typical of a Jupiter-sized planet. A dip of that magnitude would require an object much larger than a planet blocking the star's light. Alternatively, it could be many smaller objects passing together. 2 years later, in 2013, the star dipped even more dramatically, losing 22% of its brightness. For context, if a planet the size of Jupiter passed in front of the Sun, the brightness drop would be about 1%. To block 22%, an occulting body would have to be nearly as large as the star itself, an impossibility for planets. The sheer depth of the dimming forced astronomers to think beyond the planetary paradigm. Not only were the dips deep, they were irregular. Typical transits repeat like clockwork, revealing the orbital period of the planet. But the dips in Tabby's star occurred at uneven intervals, with some separated by days, others by hundreds of days. The lack of periodicity suggested that whatever was causing the dimming was not in a stable, repeating orbit. The shapes of the dips were also strange. Some were symmetric, with smooth declines and recoveries reminiscent of a planet transit. Others were jagged or asymmetrical, with sudden drops and gradual returns, or vice versa. The durations varied from a few days to nearly 90 days. Such diversity in shape and length is not seen in simple planetary systems. To further complicate matters, the dips did not line up with one another in any obvious way. If one imagined a collection of planets or moons, their orbits would produce a sequence of dips with a repeating pattern, perhaps with overlapping curves. No such pattern emerged. Each dip seemed to be its own event, independent of the others. Astronomers looked for evidence of a ringed planet or a group of co-orbital bodies, such as Trojan asteroids trailing or leading a planet. In some systems, a large planet with extensive rings could cause complex light curves. But simulations showed that the depth and irregularity of Tabby's star's dips could not be reproduced by rings alone. The timing and amplitude did not match any plausible orbital configuration. Another idea considered was that the star might have an exotic exomoon system. Large moons transiting after their planet could produce secondary dips, adding structure to the light curve. However, such systems would still produce a repeating pattern tied to the planet's orbit. Again, the irregularity of the observed dips ruled out this scenario. The star's baseline brightness also showed signs of gradual change. In addition to the deep, short dips, Kepler data revealed a long-term dimming over the 4 years of observation. The star's brightness decreased by about 2% across those years. After this slow fade, a rapid fade occurred, followed by another slow decline. No known planet or group of planets could account for such long-term trends. At first, some suggested the long-term dimming might be an artifact of the instrument or of data processing. Historical photographic plates from the 20th century seemed to show a century-long dimming, amplifying the sense of mystery. Later analyses, however, suggested that differences in instrumentation and calibrations were to blame. Still, the Kepler-era dimming remained real and unexplained. The fact that no other star in the Kepler field exhibited similar behavior made Tabby's star stand out even more. Among the thousands of light curves studied, none displayed such deep, irregular dips combined with a long-term fading trend. This uniqueness suggested that the star was either an outlier of an extreme astrophysical process or that something else entirely was happening. The star does have a faint red dwarf companion, about 2 arc-seconds away. But this companion is far too distant and dim to cause the observed dips directly. Its gravity could, in principle, perturb comets or debris into the line of sight, but it cannot block the star's light. Thus, the presence of the companion adds a potential complicating factor, but does not explain the light curve. When confronted with data that defy expectations, astronomers often look first for prosaic explanations. Could the dips be due to instrumental noise? Could Kepler have been mispointed? Checks of the spacecraft's pointing and of other stars in the same field showed no anomalies. The dips appeared only in the light curve of Tabby's star. Next, scientists considered whether the star itself could be undergoing intrinsic variability. Some stars undergo eruptions or pulsations that cause significant changes in brightness. However, Tabby's star is a normal F-type star, not known to pulsate on such short timescales. Spectroscopic observations showed no signs of unusual stellar activity. Its spectrum lacked the emission lines associated with flares or accretion. Star spots, which cause periodic modulations as the star rotates, were also considered. Tabby's star rotates every 0.88 days, causing slight variations on that timescale. But the large, irregular dips occur on much longer timescales and do not align with the rotation period. Thus, star spots cannot produce 20% dips lasting weeks. Even exotic scenarios like stellar mergers or interactions with unseen companions were explored. A close stellar encounter could disrupt a disk of material, leading to temporary dimming. Yet such encounters are rare and would leave other signatures, such as infrared excess or radial velocity variations. Observations found no such evidence. The light curve of Tabby's star therefore stands apart from the patterns produced by planets or stellar variability. Its dips are too deep and irregular to be caused by normal transits. Its long-term dimming does not fit the profile of known stellar activity. The puzzle invites us to think beyond the familiar categories of astrophysical phenomena. One might ask whether multiple planets could conspire to produce such irregularity. Perhaps a planet broke apart, creating a cloud of debris that orbits irregularly. Or perhaps there are several objects on eccentric orbits that occasionally line up to produce deep dips. These possibilities were modelled, but none fit the data sufficiently. The irregularity remained. The unusual depth of the dips also challenges our intuition about solid bodies. Planets and moons are opaque objects with well-defined cross-sectional areas. To block 20% of a star's light, an object would need to be comparably large. But such an object cannot be anything other than another star, and a star passing directly in front would be immediately evident. No such companion was seen. This realization led to the idea that perhaps many small things, rather than one big thing, were blocking the light. A swarm of objects, each too small to be detected individually, could collectively cover a significant portion of the star. The challenge would then be to explain why such a swarm existed, and why it passed in front of the star at irregular intervals. This line of thought led to the first set of hypotheses that tried to reconcile the light curve with natural phenomena. While puzzling over these patterns, the astronomical community experienced a mixture of excitement and caution. A star that does not behave like the others is a rare treasure, but it also demands restraint in speculation. The data did not match planets, so attention turned to dust, debris, and comets. Yet each idea had to be weighed against the absence of infrared excess, the depth of the dips, and the irregular timing. As word of Tabby's star spread, the public imagination leaped ahead. Suggestions of artificial megastructures, of Dyson spheres, and alien engineering emerged in the cultural conversation. Astronomers, however, focused on natural explanations first, guided by the principle that extraordinary claims require extraordinary evidence. The next chapters will delve into these natural hypotheses, starting with swarms of comets and catastrophic collisions. But before moving on, let us pause to appreciate the discipline involved in rejecting simple explanations. It would have been easy to attribute the dips to an unusual planet and move on. Instead, the data drove scientists to explore new models and possibilities. This willingness to be puzzled is one of the hallmarks of scientific discovery. In the absence of periodicity, astronomers used every available tool to characterize the star. Spectroscopy provided temperature, gravity, and metallicity, confirming that Tabby's star was normal. High-resolution imaging ruled out close companions that could contribute additional light. With each negative result, the field of plausible explanations narrowed. Still, the star's light curve remained an invitation to wonder. Its dips challenged models of planetary transits, dust disks, and stellar variability. Its uniqueness among thousands of stars suggested a rare event or configuration. The stage was set for a cascade of hypotheses, each seeking to explain how a normal star could produce such an abnormal light curve. As we leave behind the comfortable patterns of planetary transits, we carry with us the knowledge that Tabby's star is not like a planet-bearing system. In the next chapter, we'll explore the first major class of hypotheses that arose to explain its flickering. The idea that a swarm of comets or a collision of icy bodies might be casting shadows across the star. The journey will take us from the inner edges of the star's habitable zone to the icy outskirts of hypothetical Oort clouds. Our curiosity will be tempered by the evidence. The absence of excess infrared light, the impossibility of large solid bodies, and the necessity for a plausible source of many small objects. Yet we will see how even incomplete hypotheses can illuminate the possibilities. The star's behavior invites us to imagine cosmic catastrophes and cascading debris, each with its own signature in the light curve. By comparing these ideas to the data, we hope to separate the probable from the fanciful. Even if the comet swarm hypothesis ultimately falls short, it contributes to our understanding of what is possible around other stars. In science, even incorrect ideas advance the conversation. With these thoughts in mind, we turn to the early hypotheses that attempted to make sense of a light curve that refused to be ordinary. Our exploration of irregular dips and the failure of planetary explanations also serves as a reminder that nature often defies categorization. Tabby's star is a case study in humility, showing us that our frameworks are incomplete. The pursuit of understanding continues, not because we expect easy answers, but because the mystery itself is an invitation. As we proceed, the narrative will grow more speculative, yet always grounded in the data captured by patient instruments. In the next stage of our journey, we will venture into the realm of icy debris and violent collisions, exploring how these processes might produce the striking features seen in Tabby's star's light curve. The star's flickers will guide us, and our curiosity will propel us forward into the cosmic cold. The first major hypothesis to account for the strange light curve of Tabby's star invoked swarms of comets. Comets are icy bodies that originate in the outer reaches of a planetary system. In our own solar system, they reside in the Oort cloud, a vast sphere of small, frozen objects at the edge of the sun's gravitational influence. Occasionally, a passing star or galactic tide perturbs these objects, sending them inward toward the sun. Astronomers imagined a similar scenario around Tabby's star. Perhaps a nearby red dwarf companion, or a passing star, disturbed the star's hypothetical Oort cloud, sending a cascade of comets inward. As these comets approached the star, their icy surfaces would sublimate, producing tails and fragments. If hundreds or thousands of such comets crossed the line of sight, they could collectively block a significant fraction of the star's light. This idea was attractive for several reasons. Comets are common, and their fragility can produce complex clouds of debris. The irregular timing of the dips could be explained by irregular orbits of comets falling toward the star in groups or trains. Comets also produce dust that could persist and cause additional dimming. A swarm of comets could, in principle, create the variety of dip shapes and depths observed. Such a scenario might unfold after a gravitational disturbance. If the star has a distant companion, its gravity could disturb the Oort cloud every few thousand years. Alternatively, a passing star could have passed near Tabby's star, sending a wave of comets inward. The resulting influx of icy bodies could last decades or centuries, depending on the reservoir and the dynamics. As comets approach a star, they begin to warm. Sublimation of ice produces gas and dust, forming a coma and tail. This material, though thin, can stretch over hundreds of thousands of kilometers. When the comet passes between us and the star, its coma could block light. If many comets pass in quick succession, the combined effect could produce a deep, complex dip. The irregular shapes of the dips might be explained by the changing orientation and structure of comet tails. A comet's tail points away from the star, shaped by solar wind and radiation pressure. Depending on our viewing angle, the tail could be in front or to the side of the nucleus during transit. This geometry could produce asymmetric dips with steep ingress and gradual egress, or the reverse. The idea of comet swarms gains some support from the presence of the star's faint red dwarf companion. Such a companion could gravitationally disturb material in the outer reaches of the system. If an orbital resonance or close approach occurred thousands of years ago, it could send comets into the inner system now. This scenario would be rare, explaining why only one star among thousands exhibits such behavior. However, the comet swarm hypothesis faces significant challenges. To block 20% of the star's light, a tremendous amount of material would be required. Models showed that one would need hundreds of comets of 200 kilometers in diameter, or thousands of smaller ones. Such a swarm would be unprecedented, and it is unclear whether any Oort cloud could supply so many large bodies. Furthermore, cometary material is rich in volatile ices and dust. As a swarm of comets sublimates, it should produce an infrared excess, an increase in infrared light emitted by the heated dust. Infrared observations of Tabby's star, however, show no significant excess. This absence of warm dust argues against a massive cloud of comets. Another difficulty arises from the shape of some dips. Some dips in Tabby's star's light curve are symmetric, with gentle declines and rises. Such symmetry is hard to reproduce with comet tails, which produce asymmetric profiles due to the direction of the tail. While multiple comets could smooth out irregularities, simulations struggle to produce the precise shapes observed. The timing of the dips also raises questions. If a train of comets were responsible, we might expect a sequence of dips with decreasing depth as the comets disperse and sublimate. In Tabby's star, the deepest dip occurred after several shallower ones. This sequence is hard to reconcile with an infalling swarm, which would likely produce the largest event first. Nevertheless, the comet swarm hypothesis remains part of the conversation because it offers a natural mechanism for multiple small objects to block light. It invites us to consider the chaotic outskirts of planetary systems and the rare disturbances that send comets inward. Even if the specifics do not fit perfectly, the idea forces us to think about the dynamic evolution of debris. Beyond comets, some researchers considered the possibility of a catastrophic collision between planetary bodies. Imagine two large planets, or planetesimals, colliding in the inner system of Tabby's star. Such an impact would release vast quantities of dust and debris, forming a shroud that orbits the star. As this material crosses our line of sight, it could cause deep, irregular dips. Collisions are not purely speculative. In our own solar system, the leading explanation for the formation of the Moon is a giant impact between Earth and a Mars-sized body. Such impacts can occur during the final stages of planet formation or during later dynamical instabilities. When they do, the aftermath can be dramatic, producing hot, glowing debris disks. A debris disk from a collision would initially be hot, emitting strongly in infrared. Over time, the debris would cool, and the particles would spread out. As they spread, they could form clumps or clouds that cause irregular dips. The shapes of the dips could reflect the distribution of particle sizes and the evolution of the debris cloud. However, collisions involving large bodies should produce significant infrared excess, detectable by telescopes. Observations of Tabby's star show no such excess. This argues against a recent giant impact. The absence of warm dust means that if a collision occurred, it must have been long enough ago for the debris to cool, but then the dips should have also diminished. Another possibility is that the collision involved smaller bodies, such as asteroids or comets. When the dwarf planet-like object Ceres was struck by large asteroids in our solar system, debris was ejected. On a larger scale, a collision between two comet-like bodies could release dust without producing large amounts of infrared radiation. Still, producing a 20% dip would require a lot of material. Some scientists propose that a tidal disruption event could be responsible. In this scenario, a large planet or brown dwarf comes too close to the star and is torn apart by tidal forces. The resulting stream of debris could form a cloud that orbits the star, occasionally passing in front. This could produce deep dips and irregular timing. Tidal disruptions can occur in extreme gravitational environments, such as near black holes. Around a main sequence star, a planet would have to be on a very eccentric orbit to approach closely enough to be torn apart. Such an orbit would be unstable, and the disrupted material would likely settle into a disk, again emitting infrared light. The lack of infrared emission argues against this scenario. Another early idea was that we were witnessing the aftermath of an exomoon breakup. If a large moon were torn from its planet and fragmented, the resulting debris could form clumps and streams. These could produce multiple dips of varying depths as different fragments pass in front of the star. This idea parallels the concept of comet swarms, but invokes a different source. The exomoon disruption hypothesis is intriguing, especially given the possibility of large moons around giant planets. However, it faces the same challenge, producing deep dips without infrared excess. Additionally, such an event would likely be rare and catastrophic, again raising the question of why we are seeing it now and not in other systems. Despite these challenges, the comet and collision hypotheses provided a framework for thinking about multiple small objects causing the dips. They moved the conversation away from singular planetary bodies toward ensembles of debris. They also highlighted the importance of infrared observations, which can detect dust and warm material that might otherwise be invisible. Some researchers attempted to reconcile the lack of infrared excess by suggesting that the obscuring material might be cold, located far from the star. If a collision occurred at a great distance, the debris would be cool and emit little infrared light. However, for the debris to block the star's light, it would still need to cross our line of sight. The geometry of such a scenario is unlikely. Others suggested that the material might be transient and composed of large chunks with little dust. Large chunks would block light without producing much emission, yet such chunks would have to be numerous and precisely aligned to account for the complex dips. The probability of this alignment is low, making the idea less convincing. Another variant considered was that the star might be consuming a planet. As a planet spirals into its host star due to tidal interactions, it is heated and evaporated, producing clouds of material. This process, while dramatic, would likely produce a gradual dimming rather than discrete dips. Moreover, it would leave spectroscopic signatures that were not observed. Each collision or disruption scenario has to contend with the observation that the dips are irregular but recur over years. If a singular event produced the debris, we might expect the dips to diminish over time as the material dissipates. Instead, after the deep dips in 2011 and 2013, the star seemed to settle until similar events were observed years later. This suggests ongoing or repeated events rather than a single collision. One of the strengths of the comet hypothesis is that comets can arrive in multiple groups over extended periods. A disturbance could send comets inward at different times, producing dips separated by years. Collisions, on the other hand, are more likely to be singular events. Thus, from a timing perspective, comets appear more plausible, though still problematic. Ultimately, neither comets nor collisions can fully account for the observations, the absence of infrared excess, the depth of the dips, and the irregular timing present hurdles. Still, the exploration of these ideas enriched our understanding of the processes that can occur around stars. It also underscored the need for more data and for alternative hypotheses. While the comet and collision hypotheses were being debated, astronomers continued to monitor Tabby's star. Each new observation offered a chance to test the predictions of these models. Infrared observations looked for warm dust. Spectroscopy searched for gas signatures. Photometry continued to watch for new dips. The star became a focal point for multi-wavelength study. In tandem, theoretical work explored the dynamics of comet swarms. Computer models simulated the gravitational influence of a companion star on a cloud of icy bodies. They tracked the fragmentation and sublimation of comets, predicting the resulting light curves. These simulations provided valuable insights, even if they did not solve the mystery. The debate over comets and collisions also drew attention to the complexity of stellar environments. Planetary systems are not static. They evolve over billions of years. Collisions, migrations, and disruptions shape their architectures. In studying Tabby's star, astronomers were reminded that unusual events can occur and that our catalogue of possibilities must remain open. As the comet and collision ideas struggled, other hypotheses rose to prominence. One of these involved clouds of fine dust, potentially produced by smaller debris or ongoing processes within the star's system. Dust could produce wavelength-dependent dimming and irregular shapes without requiring large bodies. This dust hypothesis will be the focus of the next chapter. Before moving on, it's worth reflecting on how the early hypotheses reflect our tendency to look for natural, known processes first. Comets and collisions are part of our cosmic experience. They invite analogies with Halley's Comet or the asteroid belt, grounding the mystery in familiar terms. Even when they fall short, they serve as stepping stones toward more subtle explanations. The discussion of comets also highlights the interplay between gravitational dynamics and observational signatures. The idea that a distant companion could perturb a cloud of icy bodies is compelling, but it requires precise conditions. The star's companion must be at the right distance and mass. The distribution of comets must be dense enough, and the timing must align with our observations. Such fine-tuning makes the scenario less likely. Collisions, meanwhile, remind us of the violence inherent in planetary formation and evolution. Worlds are built by accumulation and shattered by impacts. The story of Tabby's star invites us to imagine these cataclysms playing out around distant suns. Even if collisions are not responsible, the possibility enriches our appreciation of the dynamic cosmos. In the end, the early hypotheses of comet swarms and collisions provided an initial framework for exploring the mystery. They reflected our understanding at the time and our willingness to invoke dramatic events to explain dramatic data. As we transition to the next hypothesis, we carry with us the lessons learned. The importance of infrared observations, the challenge of matching depth and duration, and the need to account for irregular timing. The story of Tabby's star is not just about a single star. It is about the process of science itself. Hypotheses are proposed, tested against data, and refined or discarded. Each hypothesis, even if incomplete, narrows the field and clarifies what we know. The comet and collision hypotheses exemplify this process, guiding us toward a better understanding of what the mystery is not. With the stage set and the early ideas explored, we now turn to the hypothesis that gained traction as more data accumulated. That clouds of fine dust, rather than icy bodies or catastrophic collisions, might be responsible for the star's flickering. This idea offers a new perspective on the nature of the obscuring material and the mechanisms that could produce it. In the next chapter, we will delve into the dust hypothesis, examining how small particles can block light in wavelength-dependent ways. We will see how this idea addresses some of the challenges faced by the comet and collision scenarios, and we will explore how it, too, both illuminates and complicates the mystery of Tabby's star. Dust is ubiquitous in the cosmos, yet it often goes unnoticed. Tiny grains of silicate and carbon float between stars, drift around planets, and form the raw material of future worlds. Around young stars, dust forms disks that eventually coalesce into planets. Around older stars, dust can be released by collisions or sublimation. Could dust be the key to Tabby's star's mystery? The idea that dust might be responsible gained support from observations across different wavelengths. If large, opaque objects blocked the star's light, the dimming should be the same in visible and infrared light. However, observations showed that the star dimmed less in the infrared than in the ultraviolet. This wavelength dependence suggests that small particles, which scatter and absorb light differently at different wavelengths, are involved. Imagine sitting under a beach umbrella. The umbrella blocks much of the sunlight across all colors. But if you watch a sunset, dust in the atmosphere scatters blue light, letting more red light through. The same principle applies to Tabby's star. Fine dust grains scatter shorter wavelengths more effectively, leading to stronger dimming in blue light than in red or infrared. This pattern is precisely what some observations of Tabby's star revealed. When the star dipped, it dimmed more at shorter wavelengths than at longer ones. Such behavior aligns with a cloud of small dust particles passing between us and the star. Large objects would cause achromatic dimming. Small particles produce chromatic dimming. The data thus point toward the latter. A detailed analysis by Meng and colleagues in 2017 concluded that only very small particles could produce the observed wavelength-dependent dimming. They proposed that particles only a few micrometers across were responsible. These particles would not emit much infrared radiation, explaining the lack of excess detected. The dust might be arranged in a ring or clumps that occasionally obscure the star. NASA's Jet Propulsion Laboratory reported on this study, noting that the pattern of dimming across wavelengths favored the dust explanation. The researchers suggested that the dust could be orbiting the star with a period of roughly 700 days. If the dust cloud is uneven, with denser and thinner regions, it could cause irregular dips as the star moves behind different parts of the cloud. This dust cloud might originate from disintegrating comets, collisions of small bodies, or the evaporation of volatile material. Once released, the dust would orbit the star, slowly dispersing under the influence of radiation pressure and stellar winds. Over time, the cloud would thin, but if new dust is continually supplied, it could persist for years. One advantage of the dust hypothesis is that it can produce deep dips without requiring large solid objects. A high optical depth can be achieved with many small particles spread over a wide area. Depending on the density and distribution, the dust can block 20% or more of the light in some regions, while allowing most light through in others. This can create the variety of dip depths and shapes seen in the light curve. Dust can also produce irregular timing. If the dust is clumpy and orbiting on an eccentric or inclined path, it may not cross the star's disk at regular intervals. Interactions with the star's radiation and wind could change the dust's orbit over time, leading to unpredictability. Thus, dust offers a natural mechanism for irregular, deep dimming without periodicity. Another feature of the dust hypothesis is that it can explain the star's overall dimming trend. If more dust is added to the system over time, the baseline brightness will decrease. This could account for the gradual fading observed during the Kepler mission. Occasional denser clumps would produce the sharp dips. The star could then slowly brighten as the dust dissipates, aligning with the observed pattern of fading and recovery. However, the dust explanation is not without challenges. One question is the source of the dust. To maintain a substantial cloud, dust must be continuously supplied. Comet disintegration is one source, but as we have seen, the number of comets required is very large. Collisions of small bodies could produce dust, but collisions on that scale may be rare. Another challenge is the stability of the dust cloud. Radiation pressure from the star will push dust particles outward. Smaller particles are pushed more strongly and may be ejected from the system, while larger particles spiral inward. To maintain a cloud in orbit, there must be a balance of forces or a continuous replenishment of material. Without such a supply, the cloud would dissipate too quickly to produce multiple dips over years. Some researchers suggested that the dust might originate from an uneven ring around the star. Perhaps the star once had a circumstellar disk, and remnants of that disk formed a ring. If the ring is eccentric and warped, it could produce irregular dips when our line of sight intersects thicker sections. The ring might be the leftover of a disrupted planet or a remnant of the star's formation. An uneven ring can also precess, changing its orientation over time. As it precesses, different parts of the ring come into view, altering the pattern of dips. A precessing ring could thus produce quasi-periodic dimming, with long intervals between major events. This concept offers a mechanism for the observed irregularity. In addition to ring-like structures, dust can form in the wakes of evaporating bodies. If a comet or asteroid is slowly sublimating, it may leave a trail of dust along its orbit. As the star moves behind this trail, the dust can cause a dip. Multiple bodies on different orbits could produce a complex pattern of trails, leading to irregular dimming. Because small dust particles scatter light, they can also polarize it. Measurements of the star's polarization during dips could provide clues about the size and composition of the dust. Some observations have attempted to measure changes in polarization during dips, but results remain inconclusive. The faintness of the star and the subtlety of the effect make it difficult to draw firm conclusions. The dust hypothesis gains support not only from the wavelength dependence, but also because it avoids the need for large, opaque objects. It fits within known astrophysical processes. Comets, collisions, and sublimation all produce dust. Yet it still requires a mechanism to produce and sustain enough dust to create 20% dimming. The amount of dust needed is significant, and the frequency of dips suggests ongoing replenishment. Another line of inquiry considered the possibility that the dust might not be local to the star at all. Perhaps we are observing interstellar dust clouds passing between us and Tabby's star. Such clouds could contain denser regions that cause dimming. However, interstellar clouds would likely cause dimming in many stars along similar lines of sight. No such widespread dimming has been observed, making this explanation unlikely. Similarly, Some suggested that the dimming might be due to dense, non-uniform clouds in the outer solar system, or between us and the star. This is improbable, as there is no known population of local clouds dense enough to produce such effects. Additionally, such clouds would leave signatures in the light from other stars in the same region, which we do not see. The dust cloud hypothesis also intersects with the comet hypothesis. If comets are sublimating, they can produce dust that lingers and creates dimming events. In this way, comets may be the source of the dust, even if the bulk of the dimming is due to dust, rather than the comets themselves. This hybrid idea retains the gravitational perturbations needed to send comets inward, but shifts the focus to the dust they produce. One study proposed that the dust cloud might have a roughly 700-day orbit around the star. If the orbit is eccentric, the cloud would spend more time far from the star and less time near it. When it approaches periastron, the point closest to the star, it could produce the observed dimming. The irregularity arises from the cloud's uneven structure and from gravitational interactions with other bodies. Dust can be shaped by the star's magnetic field. In our own solar system, the solar wind and magnetic field create structures like the heliospheric current sheet. Around Tabby's star, a magnetic field might guide charged dust grains into specific regions or cause them to clump. This could lead to irregular dynamic patterns of dust that align with some of the dips. Another possibility is that the dust originates from the star itself. Some stars undergo mass loss, shedding material in winds or outbursts. If Tabby's star were losing material sporadically, the ejected dust could form clouds that pass through our line of sight. However, F-type stars like KYC 8462852 are not typically known for strong winds or outbursts. Spectroscopy shows no signs of such activity. As with the comet hypothesis, the dust model must contend with the absence of comparable behavior in other stars. If dust clouds of this nature were common, we might expect to see similar light curves in other systems. The uniqueness of Tabby's star suggests either a rare event or an unusual configuration. This rarity could point to a transient phenomenon, perhaps triggered by a specific disturbance. Despite its challenges, the dust hypothesis remains one of the leading natural explanations. It aligns with the wavelength-dependent dimming and the lack of infrared excess. It can produce deep, irregular dips without requiring large objects. And it offers a framework for connecting the star's gradual fading with intermittent events. Because of these factors, many researchers consider dust to be a promising avenue. Ongoing observations continue to test the dust scenario. Photometry at multiple wavelengths examines how dips vary with color. Infrared observations search for subtle excesses that might hint at dust emission. Spectroscopy looks for gas absorption lines that could accompany dust. Each data point refines the models and constrains the possibilities. Dust is not a monolithic substance. Its properties depend on its composition, size distribution, and shape. Silicate grains scatter light differently from carbonaceous grains. Irregular, fluffy aggregates scatter differently from compact spheres. Modeling the optical properties of dust is complex, and different choices can lead to different predictions. This complexity adds uncertainty to the dust hypothesis. Another aspect to consider is how dust might interact with the star's radiation. Radiation pressure can drive a dust grain outward, but if the grain is large enough, gravity can keep it bound. The ratio of radiation force to gravity depends on the particle's size and composition. In some cases, this ratio can cause dust to spiral inward or outward. The dynamic evolution of dust is thus sensitive to the specifics of the environment. If dust is responsible, we might expect the dips to exhibit similar chromatic trends across time. In some observed dips, the color dependence seems to vary, with some events showing stronger chromaticity than others. This suggests that the properties or distribution of dust may change over time. Perhaps different sources contribute at different times, or the grain sizes evolve as they collide and fragment. The dust hypothesis also leaves open the possibility that multiple mechanisms are at play. Perhaps some dips are caused by dense clouds of dust, while others are due to fragments of larger bodies. The star's environment could host a variety of transient structures, each contributing to the overall pattern. This layered complexity may be necessary to explain the full range of observations. In pursuing this hypothesis, researchers employed models of dust rings, clumps, and streams. They simulated light curves under various assumptions about the particles and orbits. Some models could reproduce certain dips, but not others. This partial success highlighted the challenge. The observed behavior may not be the result of a single, simple structure. Instead, it may reflect a combination of factors. Another intriguing idea is that the dust might be associated with a disintegrating planet. Hot, close-in planets can evaporate, shedding material that forms a tail. Such evaporating planets have been observed around other stars, producing shallow, asymmetric transits. If a larger body around Tabby's star were disintegrating, it could produce a mixture of dust sizes and a range of dip depths. Yet the required scale of disintegration is immense. Ultimately, the dust hypothesis illustrates the power and limitation of our models. Dust can produce many of the features observed, but the details remain elusive. The irregularity, depth, and evolution of the dips challenge any single explanation. As new data arrive, the dust hypothesis will be refined or replaced. But for now, it serves as a leading contender. The study of dust around Tabby's star also connects to broader astrophysical questions. Dust plays a crucial role in planet formation, star evolution, and the chemistry of galaxies. By examining dust in an unusual context, we learn more about how it behaves under different conditions. Tabby's star, therefore, serves as a laboratory for studying dust dynamics in a regime we have not encountered before. Moreover, the dust hypothesis continues to inspire observational campaigns. Citizen scientists contribute by monitoring the star's brightness, while professional astronomers plan coordinated multi-wavelength observations. This collaborative effort ensures that when the next dip occurs, we will be ready to capture as much data as possible. Only through such sustained engagement can we hope to disentangle the contributions of dust and other phenomena. As we move forward, we must remember that the dust hypothesis, like the comet and collision hypotheses, is part of a broader exploration. It represents our attempt to make sense of a mystery using the tools we have. Whether it proves correct or not, it will leave us with a deeper understanding of how light interacts with small particles and how such interactions can mimic more exotic phenomena. In the next chapter, we will see how the mystery deepened with more data. Early interpretations, based on limited observations, gave way to new questions as additional dips and long-term trends emerged. The story did not settle into a single explanation. Instead, it became a living puzzle, evolving with each new observation and challenging our assumptions. The dust hypothesis, therefore, serves as both a possibility and a prelude. It offers a partial answer, but also exposes the limitations of our current understanding. By exploring it thoroughly, we prepare ourselves for the surprises yet to come. The light of Tabby's star will continue to flicker, and with each flicker, the mystery will grow richer. With these thoughts, we close our exploration of cosmic dust for now. We have seen how fine particles can sculpt light curves, how they might arise and behave, and how they fit into the broader tapestry of hypotheses. The next chapter will take us deeper into the story of Tabby's star, revealing how new data turned the mystery into a living puzzle that continues to unfold. As the initial excitement around Tabby's star subsided, researchers continued to gather data. Each new observation had the potential to confirm or refute the competing hypotheses. Rather than resolving the mystery, the additional data deepened it. The star proved to be a living puzzle, changing before our eyes and resisting simple answers. Long-term monitoring revealed that the star's brightness continued to vary beyond the Kepler mission. After the deep dips of 2011 and 2013, the light curve showed a gradual dimming over years, then a plateau, then another decline. Some analyses suggested the star had dimmed by almost 3% over the course of the Kepler observations. This slow fade was superimposed on the sharp dips, adding another layer of complexity. The suggestion that the star had been dimming over a century emerged from a study of archival photographic plates. Researchers compared the brightness of Tabby's star over the 20th century and concluded that it had faded significantly. This dramatic claim captured the public imagination. If true, it would imply a long-term process of obscuration or intrinsic fading. However, subsequent analyses pointed out that differences in plates, emulsions, and calibrations might have produced an artificial trend. When the century-long dimming claim was re-evaluated, it was found that the evidence did not support a continuous decline. Nonetheless, the star's behavior during the Kepler era remained unusual. The combination of slow dimming and sudden deep dips had no precedent. Whatever mechanism was at work needed to account for both. This requirement narrowed the field of plausible explanations. The next major twist came when the dips returned after the Kepler mission. In 2017, ground-based observatories detected a new series of dips. These were smaller than the deepest Kepler dips, but still significant, with decreases of a few percent. The return of the dips confirmed that the phenomenon was ongoing and not confined to the 4-year Kepler window. It reignited scientific and public interest. These new dips were observed by an international network of telescopes. The Las Cumbres Observatory, a network of automated telescopes around the world, played a key role in capturing continuous coverage. Amateur astronomers also contributed, pointing their personal telescopes at the star and sharing data. This collaborative effort ensured that no dip would be missed, and it highlighted the power of citizen science. The 2017 dips, nicknamed by the team with playful names like Elsie and Celeste, had different shapes and depths. Some lasted several days, others longer. Their chromatic behavior varied, with some dips showing stronger color dependence than others. These variations provided new data to test the dust hypothesis and other models. The star, once again, defied simple categorization. As observations accumulated, it became clear that the star's behavior was not just a single phenomenon repeating. Instead, it appeared to involve multiple processes. Some dips were sharp and deep, others were shallow and broad. Some were chromatic, others were less so. The baseline brightness continued to change slowly. These layered complexities forced theorists to consider combinations of mechanisms. One emerging idea was that the star's environment might be populated by both dust clouds and larger fragments. Some dips could be caused by dense dust clumps, consistent with the chromatic behavior. Others might be due to slightly larger aggregates that produce more achromatic dimming. Still others could involve gas clouds or rings. The interplay of these components could produce the observed diversity. At the same time, the possibility that the star itself might be varying regained attention. Though F-type stars are not typically variable, some mechanisms could, in principle, cause intrinsic fluctuations. One idea invoked magnetic activity cycles, akin to the Sun's 11-year cycle, modulating brightness. Another considered avalanche statistics in the star's convection zone, producing sporadic dimming. These ideas were speculative, but served as reminders that not all variability must be external. Another suggestion was that internal processes might cause changes in the star's opacity. If the star had internal mixing events or changes in its envelope, it could dim temporarily. Such events are not well documented for stars like Tabby's star, but the unusual data invite unusual ideas. Still, such intrinsic variability would likely have spectral signatures that have not been observed. The return of the dips also allowed for multi-wavelength campaigns. Observatories with infrared, ultraviolet, and radio capabilities joined in. By observing the dips across the spectrum, scientists could test the dust hypothesis with greater precision. Some dips showed clear wavelength dependence, others did not. The mixed results suggested that more than one type of material or structure might be involved. The more data came in, the more complex the models became. Instead of a single comet swarm or a single dust cloud, researchers considered multiple streams of material. Some might be on short orbits, others on longer ones. The star might be passing through a debris field inclined to our line of sight. Or there could be large structures in a precessing orbit, casting shadows at irregular intervals. Citizen scientists continued to play a crucial role. Through projects like Exoplanet Explorers and the American Association of Variable Star Observers, volunteers watched the star's light curve in real time. Their contributions helped identify dips quickly, allowing professional astronomers to coordinate follow-up observations. The interplay between amateur and professional efforts became a hallmark of the Tabby's star saga. The deepening mystery also inspired new theoretical work. Researchers explored the dynamics of dust under radiation pressure, the breakup of exoplanets, and the interaction of debris with stellar winds. Others considered more exotic possibilities, such as interstellar objects passing near the star or dark matter effects. Although many of these ideas remain speculative, they reflect the creative response to a stubborn mystery. One particularly ambitious idea was that we might be seeing a megastructure around the star. While the concept captured public imagination, scientists approached it cautiously. For such a structure to block 20% of a star's light, it would need to be enormous. It would also need to be stable and orbiting in a specific way. The lack of periodicity and the chromatic behavior of the dips argued against this idea. Nevertheless, the notion served as a thought experiment, highlighting the extreme lengths one would have to go to if natural explanations failed. Another concept involved magnetic activity cycles, causing large star spots that come and go. However, star spots typically produce periodic modulation as the star rotates. Tabby's star's dips are deeper and less regular than spot-induced variations. Spectroscopy also shows no signs of strong magnetic activity, making this explanation less plausible. The deeper the puzzle became, the more it underscored the importance of patience in science. The story of Tabby's star unfolded over years, requiring long-term monitoring and thoughtful analysis. Quick answers were elusive. Each new dip provided another clue, but also introduced new questions. The experience reminded researchers that nature does not always yield to neat narratives. In confronting this living puzzle, scientists also revisited their assumptions. They considered whether biases in data processing could produce false trends. They looked at the stability of instruments, and the influence of Earth's atmosphere. They compared observations from different telescopes to cross-check results. This meticulous approach ensured that the mystery was not an artifact of measurement. As data accumulated, the scientific community grew more comfortable with uncertainty. Rather than seeking a single definitive answer, researchers embraced the idea that multiple processes might be at play. This openness allowed for a richer discussion, blending dust, debris, and stellar physics. It also kept the public engaged, as each new hypothesis sparked renewed interest. In parallel, the story of Tabby's star influenced the design of future missions. Telescopes like TESS, designed to find exoplanets by looking at light curves, benefited from lessons learned. The need for continuous coverage, multi-wavelength observations, and community engagement was highlighted. Future observatories might be better prepared to catch and interpret unusual events. The narrative also served as a case study in scientific communication. Early media coverage sometimes leaped to sensational interpretations, focusing on megastructures and aliens. Scientists learned to balance speculation with evidence, communicating uncertainty without diminishing excitement. The collaboration between researchers and journalists evolved, reflecting a mutual respect for the complexity of the story. The mystery deepened with each observation, but it also deepened our understanding of the processes that could occur around stars. Even if Tabby's star remains unique, the exploration has broadened our perspective on what is possible. It reminded us that our catalogue of stellar behaviour is far from complete. The universe always has room for surprises. As we look back on the years of observation and debate, we see a tapestry of hypotheses woven with data. Comets, collisions, dust, intrinsic variability, and exotic structures all played roles in the conversation. Some have faded from prominence, others remain under consideration. The star itself continues to flicker, indifferent to our theories. The living puzzle of Tabby's star taught us that not all mysteries are solved quickly. Some require long-term observation and a willingness to revisit assumptions. They challenge our frameworks and push us to develop new tools. In the process, they expand the frontiers of knowledge. The story also illustrates the value of community in science. Without citizen scientists noticing the dips, the mystery might have been overlooked. Without the dedication of professional astronomers, it might have gone unstudied. Without the curiosity of the public, it might not have inspired such wide-ranging speculation. Together, these groups kept the star in the spotlight. As we prepare to move into the final chapter of this part, we carry forward the sense of an evolving narrative. The star's light continues to change, and with each change comes new data and new possibilities. The living puzzle invites us to remain attentive and curious. In the next chapter, we will revisit the moment when the light faded again, and how that event reignited scientific curiosity. The puzzle lives on, reminding us that the universe is vast and varied. It beckons us to keep watching, to keep questioning, and to accept that some mysteries may remain unresolved for a time. But it also offers the promise that with persistence, patience, and creativity, even the most confounding phenomena can eventually be understood. With these reflections, we conclude our exploration of the living puzzle for now. The star has more stories to tell, and the next chapter will take us to one of those moments when its light faded once more, drawing the gaze of astronomers around the world. In the spring of 2017, nearly 2 years after the end of the Kepler mission, the light of Tabby's star dipped again. The call went out to observers around the world. The star was fading. On social media, researchers and enthusiasts used the playful rallying cry, "Where's the flux?" as they watched the star's brightness in real time. This event marked a turning point, transforming the mystery from a historical curiosity into a live unfolding story. The new dips were first detected by the Las Cumbres Observatory Network. These telescopes, situated in both hemispheres, provide continuous coverage by handing off observations from one site to another as the Earth turns. When the first hints of dimming appeared, the network switched into a high cadence mode, capturing the star's brightness every few minutes. Soon, the data confirmed that a significant dip was underway. Astronomer Tabitha Boyajian, after whom the star was nicknamed, alerted the community. She wrote that the star was currently in a deep dip and urged colleagues to observe. Within hours, amateur astronomers across the globe turned their telescopes toward the star. Professional observatories, with capabilities in different wavelengths, joined in, planning simultaneous observations in visible, infrared, and ultraviolet light. The first dip of 2017 was nicknamed Elsie, after one of the donors who had supported the observations. It reached a depth of about 2%, less than the deepest Kepler dips, but still remarkable. The dip lasted several days before the star returned to its baseline brightness. The event's moderate depth and duration provided an opportunity to test the dust hypothesis and other models under live conditions. Observers noted that the dimming was wavelength dependent, consistent with small particles scattering blue light more than red. Infrared measurements showed less dimming, supporting the idea that dust was involved. However, the degree of chromaticity varied during the dip, hinting at a complex distribution of particle sizes or densities. This complexity kept the discussion alive. Several weeks later, another dip occurred, nicknamed Celeste. This one was shallower and shorter, but again showed a color dependence. A third, Skara Brae, followed, and then a fourth, Angkor. Each dip had its own character, with subtle differences in shape, depth, and chromatic behavior. Together, they formed a cluster of events that echoed the clusters seen in the Kepler data. The naming of dips reflected the sense of community around the star. Each name honored a person or place connected to the project. It transformed abstract data points into stories, giving each dip a personality. This human element added warmth to the scientific pursuit, reminding observers that behind the graphs and models are people united by curiosity. During these dips, researchers coordinated across continents. Some observed with small telescopes in their backyards. Others used large observatories with sensitive instruments. Communication was rapid, often via social media and email lists. Data were shared openly, allowing multiple teams to analyze the same events. This collaborative approach ensured that the dips were captured in as many ways as possible. The multi-wavelength observations proved invaluable. For Elsie, visible light showed a steady decline and rise, while infrared data showed a smaller dip. Ultraviolet observations were more noisy, but indicated a stronger dip at shorter wavelengths. Polarimetry, though challenging, was attempted by some teams to look for signatures of aligned dust grains. Spectroscopy looked for absorption lines that might indicate gas associated with the obscuring material. The results reinforced the idea that dust was playing a significant role, but they also revealed nuances. The variability in chromaticity suggested that different dips might involve different dust populations. Some might be dominated by fine grains, others by slightly larger particles. The shape of the dips hinted at structured clouds, perhaps with cores and halos. At the same time, some observers noted that the baseline brightness of the star seemed to fluctuate on longer timescales. Between dips, the star's brightness changed by small amounts, sometimes brightening slightly before fading again. These subtle variations added to the complexity of the light curve, making it difficult to establish a single baseline. The 2017 events also rekindled public fascination with the star. News outlets covered the dips, and podcasts discussed the latest observations. The idea that we were witnessing something in real time, something that might reveal its nature before our eyes, captured imaginations. Artists and writers found inspiration in the star's flickering, adding cultural layers to the scientific story. In the wake of the 2017 dips, teams published new analyses. They examined the timing and spacing of the dips, looking for patterns. Some proposed that the dips were grouped in ways that could be linked to orbital periods of dust clouds. Others saw correlations with the star's rotation, or with hypothetical companions. The results were suggestive, but not definitive. The data from 2017 also prompted a re-examination of the Kepler data. With the benefit of live observations, researchers looked back at the earlier dips to identify similarities and differences. They applied new models that incorporated dust, clumps, and streams. Some found that the shapes of the dips could be reproduced by dust clouds with steep density gradients. Others proposed that the star was occulted by a circumstellar structure that precessed, causing the pattern to repeat on a long timescale. As 2018 and 2019 unfolded, additional dips occurred. Some were shallow and barely noticeable. Others were more pronounced. The star's light continued to vary, with subtle fluctuations and occasional events. Each dip was named and studied, adding to the growing catalogue of dimming episodes. The pattern remained irregular, defying attempts to predict when the next dip would occur. In 2019, a deeper dip was observed, approaching 5%. This event, along with a series of smaller dips, resembled the pattern seen in the early Kepler data. It suggested that whatever mechanism was responsible was persistent and capable of producing a wide range of depths. The continued absence of significant infrared excess, however, remained a puzzle. Dust seemed to be involved, but the amount and temperature were difficult to reconcile. The ongoing observations also allowed for more precise tests of the dust hypothesis. Some dips showed clear evidence of wavelength-dependent dimming, while others were nearly achromatic. This variation suggested that different dips might involve different compositions or size distributions. It also raised the possibility that some dips might not be caused by dust at all. Through it all, the community's sense of wonder persisted. Each new dip was an event, a chance to learn something new. The unpredictability kept observers on their toes, ready to pivot their schedules at a moment's notice. The star had become a cosmic improviser, playing notes we could not anticipate, but to which we listened intently. The 2017 and subsequent dips underscored the importance of continued monitoring. Without persistent observation, these events would have been missed, and the narrative would have remained incomplete. The fact that the dips returned at all demonstrated that the mechanism was ongoing. Whether it involved dust, debris, or something else, it was active on timescales of years and decades. The live nature of the observations also highlighted the role of technology in modern astronomy. Automated telescopes, real-time data analysis, and global communication networks made it possible to respond quickly. Citizen scientists could access data and contribute from their homes. This democratization of observation blurred the lines between amateur and professional, creating a shared experience. The return of the dips also provided an opportunity to test more speculative ideas. Some researchers looked for periodicities in the timing of dips that might hint at orbital periods. Others searched for correlations with the star's radial velocity, looking for gravitational influences. Some even considered whether interstellar objects passing through the system could cause temporary dimming. None of these ideas gained consensus, but they enriched the discourse. As the years progressed, the stars' behavior remained enigmatic. The dips came and went, sometimes in clusters, sometimes isolated. The baseline brightness drifted slowly. The chromaticity of dips varied. The absence of infrared excess persisted. Hypotheses were refined, but none provided a complete explanation. The star, it seemed, was determined to keep some secrets. The sustained attention on Tabby's star had broader impacts. It fostered collaborations across institutions and disciplines. It inspired improvements in data analysis techniques, particularly for irregular and aperiodic signals. It encouraged the development of flexible observing schedules that could respond to transient events. These advances benefited other areas of astronomy as well. Within the community, the mood oscillated between frustration and fascination. The lack of a definitive answer could be maddening, but it was also a powerful motivator. Scientists are drawn to mysteries, and the deeper the mystery, the more compelling it becomes. Tabby's star offered a challenge that stretched minds and methods. The story of the 2017 dips and those that followed reminds us that the universe is dynamic. Stars flicker and fade, dust moves and clumps, and our understanding evolves with each observation. The excitement of watching a mystery unfold in real time is a rare gift. It connects us to the cosmos, not just as observers, but as participants in a grand narrative. As we listen to the stars flickering, we are reminded of our place in the universe. We are small beings on a small planet, gazing at a distant sun and trying to understand its whispers. The dips and fades become symbols of our curiosity and our persistence. They show that even subtle variations in starlight can captivate and inspire. The dips of 2017 and beyond did not solve the mystery of Tabby's star, but they enriched it. They provided fresh data, tested existing hypotheses, and opened new avenues of inquiry. They demonstrated the power of coordinated observation and the importance of community engagement, and they kept the star in the spotlight, ensuring that the search for answers would continue. As we conclude this part of the story, we leave the star still flickering, still mysterious. More dips may come, each offering new clues. Observers will keep watching, ready to catch the next fade. The narrative is ongoing, and the ending is not yet written. In the next part of our journey, we will explore how the mystery of Tabby's star fits into the broader quest to understand the cosmos. We will consider what the flickering light tells us about the processes that shape planetary systems and how it influences our search for other unusual stars. But for now, we remain in the moment when the light fades, our eyes fixed on a point of light that continues to defy our expectations. As our story deepens, imagination unfurls like a cosmic sail. In the quiet, after we explored the strange behavior of Tabby's star, our minds drift to visions that were once the domain of dreamers. Long before telescopes peered into distant light curves, writers imagined colossal structures, shimmering envelopes that could transform a sun's blaze into shelter and sustenance. These fantasies were not anchored in equations, but in the thrill of possibility. Yet they seeded ideas that would later be taken up by scientists. It is in these early flights of fancy that the seeds of the Dysonian dream took root. In the 1930s, novelist Olaf Stapledon wrote of civilizations evolving beyond their planets, building light traps to harvest the radiance of their stars. His epic cosmic tale envisioned beings who, to survive, constructed enormous shells of material around suns, capturing the energy that would otherwise stream out into cold space. Stapledon was not an engineer, yet he sensed that a society spread across multiple worlds would thirst for energy and would have to overcome the vastness of space. Through his story, the notion of enclosing a star entered human consciousness, a fictional blueprint for cosmic industry that would become part of our scientific lexicon. It was an early echo of a concept that still fuels our curiosity. Other storytellers soon followed. Science fiction began to fill with descriptions of ring worlds and hollow spheres, some as backdrops, others as key to plots. Writers like Larry Niven imagined a narrow band encircling a star, a ribbon wider than a planet's circumference, rich with forests and oceans, and home to millions of beings. Brian Aldiss and Bob Shaw later described similar constructs in their novels, weaving them into complex civilizations. In television and games, Dyson-like structures became backdrops for adventure. Though the physics was often glossed over, the image of an engineered star system captured hearts because it hinted at a scale of possibility beyond our own. These fictional megastructures were rarely described in detail. Authors hinted at the challenge of building them, the gravitational tugs, the unimaginable quantities of raw material. They sometimes served as MacGuffins, wonders to be sought or feared, and other times as metaphors for cosmic hubris. Yet even when they were mere scenery, they shaped how readers thought about the future. Science fiction, with its freedom to explore without constraints, prepared us to ask serious questions. Could any species really rearrange a solar system? Would such a feat ever be visible to distant eyes? The idea persisted because it was both grandiose and strangely plausible. By the middle of the 20th century, these dreams met science. Post-war optimism and a surge in space exploration invited thinkers to push at boundaries. The energy demands of an advanced civilization became more than a speculative exercise. They became a topic for calculation. If a society survived long enough to harness all the energy of a planet, what next? Would they go on to harvest more? Could they circumvent the natural limits of their star? Questions like these hovered like mirages at the edge of physics and philosophy, waiting for someone to attempt an answer. Enter Freeman Dyson, a physicist with a gift for blending imagination and rigor. In 1960, he published a short paper that would give a name to these imaginative constructs. The paper, titled Search for Artificial Stellar Sources of Infrared Radiation, proposed that advanced civilizations might build swarms of structures around their stars to capture light. Dyson wrote that a large number of independently orbiting fragments could intercept starlight and convert it into infrared emission. He was inspired by Stapledon, and he admitted that he borrowed freely from fiction. His genius lay in treating the idea with the seriousness of a thought experiment, calculating how such structures might appear to distant observers. Dyson argued that if a civilization covered its star with energy-collecting satellites, the visible light would dim, but the waste heat would radiate at longer wavelengths. Instead of searching only for radio messages, he suggested astronomers look for unusual infrared signatures that might betray alien engineering. He did not propose building such a sphere himself, nor did he imagine a rigid shell. He explicitly cautioned that a solid sphere would be mechanically impossible. The concept that later bore his name was a swarm of small habitats or collectors in orbit, an organic cloud of technology. Yet the shorthand Dyson sphere stuck, and the term was adopted widely, even against his wishes. Importantly, Dyson's motive was not to claim aliens existed, but to outline a method for detecting them. At a time when radio searches dominated, he argued that silent civilizations might still reveal themselves through their waste heat. His calculations predicted that a star's energy captured by a swarm of satellites would be re-emitted at infrared wavelengths, making the star appear anomalously bright in that part of the spectrum. In other words, you could look for a warm glow where a star's visible light was curiously faint. This pragmatic suggestion launched decades of search efforts and set the stage for the story of Tabby's star. Dyson himself was often bemused by the ensuing fascination with his idea. He noted that writers of science fiction clung to the image of a solid sphere, while he preferred the concept of a Dyson swarm. He referred to the name as a misnomer and credited Stapledon as the true originator. Nevertheless, the term had staying power. It conjured images of cosmic engineering that were irresistible to storytellers and scientists alike. In the decades that followed, Dyson spheres became shorthand for the technical aspirations of hypothetical Type II civilizations. As the idea matured, it intersected with the Kardashev scale, a measure proposed in 1964 by Soviet astronomer Nikolai Kardashev. He classified civilizations by the amount of energy they could harness. A Type I civilization used resources at the scale of its home planet. A Type II civilization could draw on the entire output of its star. Type III meant mastery of a galaxy. Dyson's swarm became a quintessential Type II project, an illustration of how to tap into stellar power. It offered a way to imagine a society that had transcended planetary limits, and it gave astronomers a potential beacon to search for. Beyond classification, the idea spurred speculation about what a star's energy could do. Harnessing all of the sun's light would provide something like 400 million times humanity's current energy consumption. You could imagine building thousands of habitats, each with its own ecosystems, effectively multiplying the surface area available for life. You could feed colossal supercomputers, run planet-sized experiments, or power propulsion systems capable of moving entire worlds. Forbes.com. The waste heat alone would surpass any natural planetary emission, making such a project stand out as an unnatural presence in a galaxy. Some thinkers proposed even more exotic uses. A Dyson swarm around a red dwarf could benefit from that star's extraordinary lifespan, lasting trillions of years, providing stability for civilizations that might plan in cosmic timescales. Forbes.com. Others imagined nested shells called matryoshka brains, where successive layers of collectors would use the waste heat of inner layers, creating a cascade of computing power. The speculation extended to star lifting, wherein a civilization might control stellar output or gradually siphon mass to prolong its star's life. These fantasies were extreme, yet they stemmed from plausible physical principles. In popular accounts, Dyson spheres became synonymous with utopian or terrifying futures. They appeared in stories as paradises with endless resources, or prisons isolating their creators from the universe. Television shows used them as settings for adventures. Computer games offered them as endgame technology. Each portrayal reflected contemporary hopes and anxieties. The real significance, however, lay in how these narratives broadened our conception of what engineering could be and encouraged scientists to think imaginatively about energy and survival. While science fiction reveled in the possibilities, practical considerations soon emerged. Engineers pointed out that no known material could form a rigid shell around a star. The gravitational and thermal stresses would shatter any structure. A swarm of satellites was more plausible, yet the scale would still dwarf anything humanity has ever built. Even breaking apart planets might not yield enough raw material. Furthermore, controlling orbital dynamics of billions of objects would require staggering precision. These difficulties did not render the idea impossible, but they underscored that Dyson spheres, if they exist, are the products of civilizations far beyond our own. The search for such constructs became part of the wider field of SETI, search for extraterrestrial intelligence. Radio telescopes scanned the sky for signals, while infrared surveys looked for unusual excesses of heat. Projects like Project Hephaistos sifted through astronomical databases to identify stars with an unexpected mid-infrared glow. Researchers filtered out natural phenomena like dust disks and galaxies, narrowing down candidates. Out of millions of stars, only a handful exhibited the right signature. None has yet been confirmed as artificial, but the method has matured. It is in this context of careful searching that Tabby's star would rise to prominence. Our story shifts from speculative engineering to an actual observation. In 2009, volunteers participating in the Planet Hunters project noticed something odd. As they examined light curves from the Kepler Space Telescope, they encountered a star whose brightness sometimes plunged dramatically. Unlike typical exoplanet transits, which cause brief, regular dips, this star exhibited irregular, asymmetric dimming events lasting days or weeks and reducing its brightness by up to 22%. It was a unique pattern that did not fit the templates used to identify planets. The volunteers flagged it for further attention, and an investigation began. The star, catalogued as KYC 8462852, would later be nicknamed Tabby's star, after astronomer Tabitha Boyajian, who led the follow-up study. Boyajian and her colleagues searched for straightforward explanations. Could it be a young star with a protoplanetary disk? No, it lacked the infrared glow typical of dusty disks. Was it a variable star exhibiting intrinsic pulsations? The spectral type and age did not match. Could transiting planets cause the dips? The shapes and depths were inconsistent. The star appeared to be a middle-aged F-type star, stable and unremarkable, except for its dramatic light curve. Boyajian's team considered more speculative natural explanations. Perhaps a family of comets, disturbed by a passing star, was swarming in front of KYC 8462852. A train of comet fragments could, in principle, block light irregularly and produce deep dips when many fragments overlapped. This idea required a huge number of large comets, far more than any previously observed, and a convenient alignment. It was judged highly improbable, but still more plausible than other scenarios. Thus, the official paper concluded with comets as the least unlikely natural cause, while acknowledging that the mystery remained. Uncertainty invites curiosity, and curiosity invites speculation. Shortly after the paper was published, Boyajian mentioned the star to her colleague Jason Wright, an astronomer who had written about searching for alien megastructures. Wright speculated privately that, among many natural possibilities, one could imagine a swarm of artificial structures, akin to Dyson's concept, causing the dimming. He warned that this should be a last resort after exhausting natural explanations. Unfortunately, media headlines condensed this nuanced discussion into sensational phrases like alien megastructure around star. In an age of rapid news, the story went viral. The narrative of Tabby's star being dimmed by an alien structure spread quickly. News outlets emphasized the extraordinary possibility and, intentionally or not, downplayed the caution expressed by scientists. Social media amplified the sensational angle. For a brief period, it seemed that every major science news site, and even mainstream media, were asking if aliens had built a giant structure around this distant star. Astronomers found themselves clarifying that, while the megastructure hypothesis was interesting, it was highly speculative, and natural explanations were more likely. Yet the notion captured public imagination because it connected real data to a familiar science fiction trope. As the buzz grew, scientists redoubled their efforts to find natural causes. Observatories around the world began monitoring KYC 8462852, and radio telescopes listened for signals. The Allen telescope array observed the star for radio transmissions and found none. Infrared observations looked for the excess heat that a Dyson swarm would emit, but detected no such signature. Meanwhile, researchers continued to propose new models, perhaps a ringed planet with its own moon swarm, or a disk of shattered planetary debris, or star-spot cycles. Each hypothesis had difficulties, yet all sought to avoid jumping to extraterrestrial conclusions. Citizen scientists remained central to the story. The Planet Hunters volunteers who discovered the dips continued to help by inspecting new data and coordinating observations. Their vigilance allowed the community to catch future dimming events in real time. When a new dip occurred, amateur astronomers around the world turned their telescopes toward the star, providing continuous coverage. The collaboration between professionals and amateurs became a hallmark of this investigation, demonstrating how distributed observation could tackle transient phenomena. One striking aspect of Tabby's star was its long-term behavior. Researchers examined archival photographic plates dating back a century and found that the star appeared to have dimmed by roughly 20% over that period. This gradual fading, if real, implied a phenomenon extending far beyond individual comet swarms. It added weight to the idea that something larger was affecting the star's luminosity. Some hypothesized that an unresolved cloud of dust or debris orbiting at a great distance could cause both short-term dips and long-term fading. Others suggested internal stellar processes not yet understood. The mystery deepened. Public fascination with the star remained high. People followed live updates on social media, waiting to see if new dips would occur. The excitement translated into tangible support. A Kickstarter campaign launched to fund a dedicated network of telescopes for continuous monitoring raised over $100,000. This citizen-funded effort allowed the research team to secure telescope time and build an alert system to notify observers when the star's brightness changed. The story thus showcased how public enthusiasm could directly support scientific research, bridging the gap between curiosity and discovery. Media attention, however, was a double-edged sword. While it drew resources and volunteers, it also fostered misconceptions. Some outlets presented the alien hypothesis as more than a remote possibility. Others simplified scientific debates into dichotomies of aliens versus not aliens. Astronomers repeatedly emphasized that they were not claiming evidence of extraterrestrial engineering. They explained that extraordinary claims require extraordinary evidence, and that speculation must be weighed against known astrophysics. Nevertheless, the narrative persisted because it resonated with our innate desire for cosmic companionship. In the years following the initial discovery, new data began to erode the case for a megastructure. Observations across different wavelengths revealed that the dimming was chromatic. Blue light was diminished more than red. Dust grains of a certain size absorb shorter wavelengths more efficiently than longer ones, so this pattern strongly suggested that whatever was blocking the star was not opaque megastructure, but fine dust. Even Jason Wright, who had suggested searching for alien structures, noted that these findings removed the main reason to invoke the Dyson idea. The data pointed toward natural material dispersed in space. Astronomers published papers showing that the star's dimming could be explained by dust clouds or debris fragments on eccentric orbits. They pointed out that a megastructure should block all colors equally. The absence of an infrared signature further argued against large energy-collecting structures. While no single natural model fit all observations perfectly, the collective evidence made alien engineering exceedingly unlikely. This shift in interpretation exemplified the scientific method. Hypotheses are proposed, tested, and refined based on data. When new information arises, we must be willing to abandon our favorite ideas. Throughout this process, a lesson was reinforced. In science, wonder must be tempered with skepticism. Speculation is valuable when it drives us to look and to think, but it must be grounded by evidence. The fascination with Tabby's star reminded us how easily hope can overrun caution. Yet it also underscored the value of transparency. By sharing data openly, the research team allowed thousands of eyes to scrutinize the light curves, increasing the chances of identifying patterns and catching new dips. This openness fostered trust and engagement. Skepticism did not extinguish wonder. Rather, it refined it. As dust models gained favor, questions remained. Where did the dust originate? Could a family of exocomets be disrupted by a passing star? Was a planet torn apart by tidal forces, leaving a cloud of fragments? Each possibility invites its own fascinating sub-story about the dynamics of distant systems. Even if aliens are off the table, the processes at work are rare and instructive. Studying Tabby's star thus expands our understanding of stellar and planetary evolution. Moreover, the experience influenced the broader search for extraterrestrial intelligence. It demonstrated that natural astrophysical phenomena could mimic the signatures we might expect from technology. This realization encourages SETI researchers to develop more robust criteria and to combine data from multiple wavelengths before drawing conclusions. It reminds us that the universe is full of surprises and that humility is essential when interpreting anomalies. While we continue to scan the sky for signs of other minds, we must remember that extraordinary claims demand extraordinary evidence. Reflecting on the journey of Tabby's star, one can appreciate the interplay between imagination and measurement. The notion of megastructures arose from fiction, was formalized into a scientific hypothesis by Dyson, and provided a context for interpreting puzzling data. The excitement it generated drew attention and resources to a real astronomical mystery. Ultimately, the evidence pointed away from alien engineering, yet the narrative enriched our cultural and scientific landscape. It showed that the boundary between science and fiction is permeable, and that both domains feed our curiosity about what lies beyond. As our narrative continues, we carry forward a sense of wonder, tempered by critical thinking. The Dysonian dream may not be realized in KYC 8462852, but the star still holds secrets. Its irregular dimming patterns, long-term fading, and resilience to simple explanations keep astronomers watching. Each new observation, each faint dip recorded by dedicated observers, contributes to a slowly evolving picture. Perhaps, with time, a natural mechanism will emerge that accounts for all the data. Or perhaps future telescopes will uncover further anomalies, rekindling speculation. Either way, the journey is as valuable as the destination. Looking back at the cultural impact of this episode, we see how quickly ideas propagate in our interconnected world. A technical paper on a peculiar star led to late-night talk show jokes, social media debates, and philosophical discussions about our place in the cosmos. This tells us that people are hungry for stories that expand their sense of the universe. It also reveals the responsibility that scientists and communicators share in framing such stories responsibly. Balancing excitement with clarity is a delicate art. The Kickstarter campaign for Tabby's star was not just about money. It demonstrated that people around the world were willing to invest in pure curiosity. Supporters came from different backgrounds, unified by the desire to participate in discovery. This communal effort helped pay for continuous monitoring, but it also built a community. When dips occurred, backers received real-time alerts and could follow along. The star became a focal point for a dispersed network of enthusiasts, illustrating how modern technology can democratize participation in science. At the same time, the events reminded researchers that extraordinary claims can have reputational costs. Some scientists worried that the alien hypothesis, however carefully framed, might undermine credibility. Others argued that withholding speculation would stifle creative thinking. The resolution came not from consensus, but from process, open debate, data sharing, and rigorous testing. Through this, the scientific community navigated the tension between imaginative ideas and cautious inference, maintaining integrity while engaging the public. The long-term dimming of Tabby's star remains a subject of investigation. Some researchers have argued that the century-scale fading could be due to systematic effects in historical photographic plates. Others point to similar dimming patterns observed in stars with dusty circumstellar disks. There is also speculation that KYC 8462852 could be part of a binary system, with a companion influencing the observed luminosity. Each of these possibilities requires new data and careful analysis, showing how one puzzle often leads to another. Beyond the specifics of this star, the Dysonian dream has broader implications. It challenges us to consider how our species might adapt to the long arc of cosmic time. If humanity endures for millions of years, our energy needs will grow. We might eventually build vast space structures, though perhaps not swarms around the sun. Concepts like orbital solar arrays, lunar power stations, and asteroid mining already hint at a trajectory toward larger-scale engineering. In this context, the science fiction visions that once seemed impossible inch toward plausibility. The Dyson sphere remains both a metaphor and a guidepost. As a metaphor, it stands for the idea of harnessing resources to transcend natural limits. As a guidepost, it directs our attention to the subtle fingerprints that advanced civilizations might leave. Even if we never find one, the search shapes our understanding of the cosmos. It forces us to develop sensitive instruments, refine our models of stellar behavior, and remain open to unexpected phenomena. In this sense, the Dysonian dream is as much about cultivating our observational capabilities as it is about discovering others. In the context of exoplanet research, Tabby's star taught us that not all transits are planets. It underscored the need to look beyond standard templates and consider a wider range of astrophysical processes. It also demonstrated the power of citizen science. The volunteers who flagged KYC 8462852 were not professionals, yet their contribution was crucial. This partnership between amateurs and professionals is likely to grow as surveys like TESS and LSST generate more data than any one team can handle. Our ability to find anomalies will depend on harnessing the collective attention of many eyes. The interplay between caution and excitement, mirrored in the discourse around Tabby's star, echoes throughout the history of science. From canals on Mars to the discovery of pulsars, anomalies have often sparked speculation about life. In each case, natural explanations ultimately prevailed. But the initial excitement advanced technology and deepened understanding. The pattern reinforces a lesson. Humility is not the enemy of wonder, but its companion. By embracing both, we navigate the thin line between fantasy and reality. As we contemplate the vastness of space, it is natural to project our own hopes and fears onto the unknown. Megastructures represent both the hope of meeting peers who have mastered their environment and the fear of witnessing technology beyond our comprehension. Tabby's star became a canvas for these projections. Even though the likely explanation involves dust, the episode invites us to ponder what signs of advanced civilizations might actually look like. Would they be obvious, like a star flickering like a candle, or subtle, like a gentle excess of heat? These questions remain open, inviting further exploration. Freeman Dyson's modest paper thus continues to ripple through scientific and cultural discourse. His suggestion to look for infrared anomalies has inspired searches across the sky. Even as his original concept is often misunderstood, his emphasis on using available data to test bold hypotheses endures. He accepted that most anomalies would have natural causes, but argued that we have nothing to lose by looking. His pragmatic optimism remains a cornerstone of SETI philosophy. It encourages us to keep our minds wide, but our methods rigorous. The story of Tabby's star also illuminates how narratives evolve. At first, the star was a curiosity among thousands of Kepler targets. When unusual dips were noted, it became an object of intense study. When speculation about megastructures emerged, it captured global attention. Later, when evidence favored dust, interest waned among general audiences, but persisted among scientists. This trajectory reflects the rhythm of many scientific stories: discovery, hype, reassessment, and quiet perseverance. Each phase serves a purpose: drawing attention, refining methods, and ultimately integrating new knowledge into the broader fabric of understanding. As we continue our journey, we carry forward not just facts, but the memory of emotions stirred. The excitement of possibility, the frustration of uncertainty, and the satisfaction of progress coexist in our narrative. These feelings are as much a part of the scientific enterprise as observations and equations. They motivate us to keep looking up, to wonder about light curves and shadows, to ask what lies beyond the next discovery. In the end, whether or not we ever find a Dyson sphere, the search enriches our experience of the cosmos. In the chapters ahead, we will return to the data, exploring models that have been proposed to explain Tabby's star's behavior. We will delve into the complexities of dust production, cometary fragmentation, and stellar variability. We will also examine the broader context of technosignatures, how they are defined, how they might be detected, and what they tell us about the search for life. The Dysonian dream, though tempered by evidence, continues to inspire these inquiries. It serves as a bridge between imagination and observation, inviting us to keep exploring the unknown without losing our grounding in evidence. The early stories of megastructures often reflected the anxieties of their eras. In some tales, civilizations built spheres to avoid cosmic cataclysms, such as gamma-ray bursts or supernovae. The structures became shelters as much as power plants. Other stories treated them as temples, monuments built to showcase the dominance of species over nature. Still others used them as warnings, with civilizations collapsing under the weight of their ambition. Through these narratives, authors explored themes of sustainability, control, and hubris. The sheer scale of a star-encompassing project served as a canvas to paint moral and philosophical questions that resonate with readers beyond the realm of science. The idea of a ring world popularized by Larry Niven in 1970 offered a different take on stellar engineering. Instead of a complete shell, Niven imagined a thin ring encircling a star, rotating to provide artificial gravity. In his novel, the ring stretched 1 million miles wide and circled a star at the Earth-Sun distance. Mountains at its edges retained atmosphere, creating a continuous habitable surface with area millions of times that of Earth. The ring was a relic of a vanished civilization, raising questions about the fate of its builders. This concept captivated readers and influenced subsequent depictions of cosmic architecture in games and television. Beyond literature, visual media embraced the concept. An episode of Star Trek: The Next Generation introduced a massive interior world surrounding a star, discovered by the crew after intercepting a distress call. The characters explored the interior, marveling at its scale and engineering. The show used the Dyson sphere as a plot device, but also to convey humility. Even in a fictional 24th century, such a construct was staggering, suggesting that human advancement would still be dwarfed by ancient builders. This sense of awe served to ground the narrative, reminding audiences that there may always be higher tiers of achievement. Video games and popular culture further cemented the Dyson sphere in the collective imagination. The Halo series depicted ring-shaped worlds used as weapons or laboratories, while strategy games like Stellaris allowed players to build Dyson spheres as ultimate achievements. In these interactive environments, megastructures became goals, rewards for long-term planning and resource management. They influenced how players thought about scaling up infrastructure, balancing energy budgets, and the sacrifices needed to reach such heights. These virtual experiences made the abstract concept tangible, encouraging players to consider the implications of harnessing entire stars. The interplay between fiction and reality is particularly evident in the way terms are adopted. Dyson sphere entered everyday vocabulary in part because it evokes an intuitive image. Yet, as Dyson himself noted, the term misled many into imagining a solid, static shell. The fictional examples often embraced this interpretation for narrative clarity. In contrast, scientists emphasize swarms or rings, emphasizing that individual satellites could be replaced or repositioned. This difference illustrates how language shapes understanding. When we imagine cosmic structures, the words we use carry weight, guiding our visualization and influencing how seriously we take an idea. Freeman Dyson's own life story adds depth to his proposal. Born in 1923, he grew up reading both mathematics and fiction. He worked on wartime innovations and later contributed to quantum electrodynamics. His ability to leap across disciplines made him comfortable with speculation. When he suggested looking for artificial infrared sources, he drew on astrophysics, engineering, and a profound sense of curiosity. He often emphasized that his ideas were meant as thought experiments. He welcomed the imaginative leaps, but insisted that ideas must be subjected to observation. This combination of playfulness and rigor underpins his enduring influence. Context matters too. Dyson's 1960 paper appeared at a time when SETI was in its infancy. Radio astronomy had just begun to reveal complex cosmic phenomena. The idea that alien civilizations might broadcast signals was compelling but untested. Dyson's suggestion offered a complementary approach: search for waste heat rather than messages. In this sense, his paper was remarkably pragmatic. He acknowledged that we might not decode foreign languages, but argued we could detect thermodynamic footprints. This shift from communication to thermodynamics broadened the search and remains an important pillar of modern technosignature research. In subsequent decades, other scientists expanded on Dyson's idea. Nikolai Kardashev's scale gave quantitative benchmarks for classifying civilizations. Carl Sagan introduced fractional types to describe gradual progress along this scale. Science fiction authors extrapolated further, imagining Type 4 or Type 5 civilizations capable of manipulating entire galaxies or universes. These frameworks inspired both excitement and caution. They allowed us to envision trajectories of technological growth, but also highlighted the enormous gaps between our current capabilities and those required to harness stars. For some, these scales became aspirational. For others, they were cautionary reminders of the hubris of projecting human desires onto cosmic timescales. With the advent of infrared astronomy, Dyson's proposal moved from theory to practice. The IRAS satellite in the 1980s and the WISE mission decades later provided all-sky surveys at mid-infrared wavelengths. Astronomers developed algorithms to identify objects with excess infrared emission relative to their visible light. This search for Dysonian technosignatures overlapped with studies of young stellar objects and dusty galaxies. Discriminating between natural and artificial sources required careful modeling. Project Hephaistos exemplifies this work by filtering candidate stars and cross-checking with optical data. The rarity of credible candidates underscores the challenge and the importance of patience. The notion of harnessing a star's energy invites questions about energy budgets and waste management. The sun radiates about 4 times 10 to the 26th watts. A Dyson swarm capturing even a fraction of this output would need to dissipate waste heat. By the Stefan Boltzmann law, re-emitted energy would manifest as infrared radiation at a temperature determined by the structure's distance from the star. Engineers must design collectors that balance energy absorption with heat rejection, ensuring that habitats do not overheat. Concepts like radiators, heat pipes, and blackbody emitters become crucial. In this way, the Dyson sphere concept forces us to confront thermodynamics on a cosmic scale. Suppose a civilization solved these engineering problems. What could they do with such power? They might run simulations of entire worlds, exploring countless evolutionary paths. They could operate propulsion systems to move planets, adjusting their star's habitable zone as it brightens. They might generate artificial magnetospheres to shield planets from stellar storms. They could power lasers for interstellar communication or defense. The possibilities are limited only by imagination and physics. When we contemplate these uses, we glimpse how far technology could extend our capabilities, and we confront how small our current achievements are by comparison. Energy isn't the only resource a megastructure could provide. A ring or swarm could collect raw materials, asteroid dust, comets, and even entire moons, processing them into habitats, machinery, and art. With near unlimited energy, material recycling becomes easier. The interior surfaces of such structures could host gardens, seas, and forests sheltered from cosmic hazards. In fictional narratives, these ecosystems are often portrayed as idyllic, but they also pose challenges: maintaining climates, supporting biodiversity, and preventing overpopulation. The interplay between abundance and stewardship becomes a recurring theme. It echoes real debates on Earth about sustainability, only scaled up to the cosmic level. For some speculative thinkers, Dyson swarms are stepping stones to even grander projects. Concepts like Shkadov thrusters propose using gigantic mirrors to reflect part of a star's radiation and produce thrust, slowly altering its motion. Others imagine capturing not just a single star, but building spheres around clusters or entire galaxies, creating megastructures on incomprehensible scales. While such ideas may seem far-fetched, they serve as thought experiments to explore the boundaries of physics and engineering. They also raise ethical questions. Should we manipulate celestial bodies for our convenience? How might such interventions affect other forms of life? These questions bring philosophy into dialogue with astrophysics. Returning to Tabby's star, it is useful to appreciate the observational landscape in which it was discovered. The Kepler mission was designed to detect planets by measuring tiny dips in stellar brightness. It monitored over 150,000 stars with exquisite precision for years, generating a dataset unprecedented in size and detail. Automated algorithms sifted through light curves, but human volunteers in the Planet Hunters project proved adept at recognizing patterns that computers missed. They spotted irregularities, flagged anomalies, and discussed them in online forums. It was this synergy between machine precision and human intuition that brought KIC 8462852 to attention. When the first paper on the star's strange behavior appeared, it sparked intense interest among astronomers. Conferences featured heated discussions about models. Research groups attempted to replicate the light curve with various combinations of dust, comets, and planetary debris. The star's location, far from the crowded plain of the Milky Way, made some models harder to reconcile. Its spectral type and temperature limited the kind of circumstellar material expected. As months turned into years, the star continued to challenge expectations. Its dips did not repeat in a predictable fashion. Each new observation added pieces to a puzzle that refused to fit neatly. The comet swarm hypothesis, though improbable, had its advocates. In this scenario, a family of icy bodies passes close to the star, sublimating and leaving behind trails of dust. A subsequent dip occurs when these dust clouds cross our line of sight. The irregular depths could be explained by varying sizes and compositions of fragments. However, to produce 22% dimming, the swarm would need to be massive, and it would have to remain confined to a small region. The number of comets required far exceeded known populations. Critics argued that a perturbation sufficient to disrupt so many comets would also leave other signatures. Another idea considered was that of a giant ringed planet, accompanied by a swarm of Trojan asteroids. As the planet transited, its rings and companions could produce multiple dips of differing depths and durations. Such a system would be akin to Saturn on steroids, with rings tens of millions of kilometers wide. Modeling showed this could reproduce some features of the light curve, yet it required fine-tuned parameters. The orbital period would need to be extremely long, making detection of repeats difficult. No infrared excess was detected to indicate such a large ring system. These issues relegated this hypothesis to the speculative end of the spectrum. Star spots and intrinsic stellar variability were also investigated. Some stars display irregular brightness changes due to large spots rotating in and out of view. However, Tabby's star is not of the type known for such behavior. Its temperature and surface gravity suggest a quiet photosphere. Long-term monitoring did not reveal the periodicity associated with rotation. A neighboring star's gravitational influence could cause tidal interactions leading to variability, but no such companion was found. Thus, while stellar activity is always a factor to consider, it did not account for the data at hand. The conversation between Boyajian and Wright that sparked public speculation is worth revisiting. It occurred in the context of brainstorming all possible explanations, no matter how unlikely. Wright suggested that if natural causes failed, one might tentatively explore the idea of artificial structures. He emphasized that such a step should be taken with caution and skepticism. Boyajian included this remark in the paper's discussion section as a nod to comprehensive analysis, not as an endorsement. The subsequent media frenzy illustrates how nuance can be lost when complex ideas are transmitted through headlines. The media landscape plays a significant role in shaping public perception of scientific discoveries. Journalists seek angles that captivate audiences, and the prospect of alien engineering around a star fit perfectly. Within days, the story appeared on major news networks, blogs, and social media feeds. Memes and jokes proliferated. Some outlets highlighted the caution expressed by scientists, while others led with bolder headlines. This divergence contributed to confusion. Many readers came away believing that scientists had discovered evidence of aliens, rather than a puzzling light curve. This misinterpretation underscores the importance of clear communication. Scientists responded with a mixture of amusement and concern. On one hand, the public interest provided an opportunity to discuss astrophysics, SETI, and the process of scientific inquiry. On the other, researchers worried that misrepresentations could erode trust. They wrote blog posts, gave interviews, and corrected misinformation. They emphasized that the community was approaching the problem systematically. They also reminded the public that curiosity-driven research often involves exploring improbable ideas, and that being open to possibilities does not mean drawing premature conclusions. The episode thus became a case study in science communication. One positive outcome of the media attention was the surge in citizen participation. Amateur astronomers and small observatories joined professional campaigns to monitor the star. People organized on forums and coordinated observations across time zones. This distributed network allowed nearly continuous coverage, capturing dips as they happened. When a new dimming event occurred, observers would post real-time updates, fostering a sense of collective discovery. The Kickstarter funding allowed the purchase of dedicated instrumentation and provided travel support for researchers to meet and strategize. The star served as a catalyst for a global collaboration. Long-term observations revealed that the star's brightness occasionally brightened as well as dimmed. This oscillation added complexity to the modeling. Researchers considered whether the star might be going through a magnetic cycle akin to the Sun's 11-year sunspot cycle. However, the amplitude and irregularity did not fit standard models. The long-term fading observed in archival data suggested something more persistent. These findings motivated further searches for similar stars, but none showed the same combination of behaviors. Tabby's star remained unique. In addition to ground-based telescopes, space observatories contributed. The Spitzer Space Telescope and NASA's Swift satellite provided infrared and ultraviolet observations respectively. Their data confirmed that the dimming was wavelength dependent. It was more pronounced at shorter wavelengths. This spectral dependence strongly implies that the obscuring material is composed of small dust grains, which scatter blue light more efficiently. Dust grains smaller than a micron could account for the wavelength pattern, whereas large solid bodies would block light equally across colors. This evidence significantly weakened the megastructure hypothesis. Interpreting the dust models poses its own challenges. Dust located close to the star would heat up and emit strongly in the infrared. The absence of such an infrared excess suggests the dust must be far away, perhaps tens of astronomical units from the star. But dust far away would take years to produce dips of the observed timescales. Some theorists propose that the dust is on highly eccentric orbits, making brief, close passages. Others suggest collisions between exocomets release dust clouds that then disperse. Each scenario must reconcile the spectral data with the timings of the dips. This intricate modeling demonstrates the complexity of interpreting distant phenomena. The case of Tabby's star invites comparison with other astrophysical mysteries. For example, the discovery of pulsars in the 1960s led to speculation about little green men. Jocelyn Bell Burnell's radio signals were so regular that they seemed artificial. Only later did researchers realize they were rotating neutron stars. Similarly, the discovery of quasars was initially perplexing. These objects emitted enormous amounts of energy from compact regions, leading to conjectures about advanced civilizations. In both cases, natural explanations eventually prevailed. The pattern illustrates how unknowns provoke imaginative hypotheses that can stimulate research without necessarily leading to extraordinary conclusions. In reflecting on the skeptical response to Tabby's star, it is useful to consider the philosophy of science. Karl Popper emphasized falsifiability. Scientific hypotheses must be testable. The megastructure idea, though compelling, is difficult to falsify because almost any light curve could be shoehorned into an alien scenario with enough creativity. Natural explanations, on the other hand, are constrained by known physics. Scientists therefore prioritize natural models, not because they lack imagination, but because they offer testable predictions. This approach does not exclude the possibility of technosignatures. It situates them within a hierarchy of plausibility. Another principle invoked is Occam's razor. Given multiple explanations, the simplest that fits the data is preferred. Dust, comets, and planetary debris are common phenomena in young systems. While KIC 8462852 is not young, these processes are nonetheless more probable than the existence of a star-encircling alien project. The probability of two independent events, an advanced civilization building a megastructure and our being lucky enough to see it in the small Kepler field, is minuscule. Thus, without additional evidence, scientists lean toward dust and debris. This reasoning underscores that extraordinary claims require not just possible explanations, but extraordinary likelihoods. Skepticism does not equate to closed-mindedness. Many astronomers involved in the study of Tabby's star are also advocates for SETI. They recognize that technosignatures could exist and are worth searching for. What they caution against is adopting an extraordinary explanation prematurely. History offers examples of biases leading to false positives. The canals on Mars, drawn by Giovanni Schiaparelli and popularized by Percival Lowell, were later shown to be optical artifacts. The Martian face imaged by Viking turned out to be a play of shadows. These lessons remind us to be careful in interpreting ambiguous patterns, especially when our desires for companionship may color perception. The broader field of technosignature research continues to expand. Scientists are exploring signatures beyond megastructures and radio signals. Industrial pollutants in exoplanetary atmospheres, laser emissions, city lights on night sides, and excessive heat from computational activity. Instruments like the James Webb Space Telescope and upcoming missions will enhance our ability to detect such signals. The Tabby's star episode has influenced this field by demonstrating that astrophysical processes can mimic technological signatures. It has prompted researchers to refine their criteria, cross-check data from multiple sources, and remain cautious in their interpretations. In this way, even a misidentification can advance a field by strengthening its methods.